Good morning, guys. Can you guys see me all right? Not sure, just a quick little camera check, I guess. Thumbs up or thumbs down, somewhere in between. Maybe you can hear me but can't see me. Hopefully both. Hopefully both. Perfect, perfect, perfect. So how have you guys been? How was reading week? It sure went by fast. You guys do anything fun? FEA? Well, that's pretty much fun, so. How was it? I got a lot of questions about the assignment, and we're going to discuss some special things about it here in a moment. But besides classes or research, anything fun for reading week or just classes and research? Minecraft. Okay, good, good, good. There was some fun to be had, and that's what I like to see. Don't stress out about classes and research, guys. You guys got lives. Make sure you guys live your lives. These are nothing compared to your lives. All right? That's your actual homework. Enjoy life. All right, so before we begin, the first thing I want to do is I just want to take a look at E-class, because after the conclusion of our last lecture, I guess, we hit the midway mark of this course, which is nice for us. So if we look at our E-class right here, we finished all the way up to lecture 5, which is solid elements. And today we're going to talk about isoparametric elements. Now, next lecture, we're going to kind of wrap things up with the Newton-Raphson method. And after that, we're basically done the theory. Now, we're technically not done the theory, but for as far as this course will go, we're done the theory. So once we get into lecture 8 with material plasticity, contacts and constraints and instability, we're going to focus more on how we can implement these in Abacus. Because things like material plasticity, those would take a whole semester just to cover the theory in itself. Those of you guys who've taken 664, the solid mechanics, you guys may be a little bit familiar with material plasticity. Probably more so with metal plasticity or steel plasticity. But once we get into concrete plasticity, that right there would take probably half the semester to teach. So when we start getting into these later subjects, it's not so much going to be about the theory, it's how can we implement these in finite element programs such as Abacus, so you guys have a kind of a good understanding of what exactly is going on. So as I said, we're at the midway mark. How are you guys feeling so far about this course? Has it been good? Has it been bad? Any feedback would be appreciated. It's my first time teaching a graduate course. Undergraduate courses are fun because the students will believe anything that you say. Like I taught Eng 130 and I can tell them garbage if I wanted to and they'll be writing it down, big smile on their faces. But graduate students are smarter than that. So how have you guys been feeling about this course? Have my methods been all right, or is there something I need to improve? What do you guys think? I'm curious. All right, perfect. So we got one enjoyment. So that's great for me. That makes me really happy. So thank you, Sabrina, for letting me know. If you guys do want to provide any suggestions, just feel free to email me. I'm happy to help answer anything you guys want. So what we're going to do is we're going to take a quick look at the assignment that's technically still due, but I don't care too much. So we're going to go over it. Now, last time, we covered solid elements. We covered the theory of solid elements and how to get the stiffness matrices of those solid elements. But if we look at our assignment here, we never actually talked about calculating those stiffness matrices. If we look at the assignment, well, this was rigid body motion, question 1. Question 2 was just purely abacus with a little bit of Euler-Bernoulli theory. But I never actually requested that we calculate the stiffness matrices of those elements by hand. Now, the reason why I didn't is because what we learned last lecture, as I kind of hinted to many times, we don't actually use that theoretical approach when we're finding these stiffness matrices. We actually do something a little bit different that makes our lives a little bit easier, and that's what we're going to talk about today. So by the end of the lecture today, you guys will know exactly what Abacus does when it's calculating the stiffness matrices of those elements. Remember, one of the things that we said when we were calculating those stiffness matrices in Abacus is we talked about the idea of full integration. That's something we never actually talked about yet, because in that pure theoretical approach, there is no such thing as full integration or reduced integration, anything like that. But by the end of this lecture, it'll make a lot more sense. So if we were to go over to assignment 5 here, well, now we're actually going to start talking about calculating the stiffness matrices. So that's what's going to happen by the end of this lecture. So you guys may have thought you got away without calculating those stiffness matrices. Well, not quite. So the next assignment, we're going to focus on calculating those matrices. But question 3, we're basically going to do together in class today. So what's going to happen is we're going to talk about the modifications that we're going to make to our elements. And then we are going to code together as a class, basically question number 3. The other 2 questions are not too bad. If we look at question 1, it's the exact same as our assignment we did before, but now we are going to use reduced integration elements. And by the end of the lecture today, you guys will know exactly what that means and what the limitations associated with those are. Now this right here, this is kind of just more for fun. This question will take you 2 seconds. Question number 2, it's just evaluating integrals. And remember, one of the things that we said is if we have an integral from -1 to 1, well, there's something very special we can do. And we're going to talk about that a little bit later. Question number 3, we are going to do together in class today, so that's not going to be a problem. And then question 4 is just a nice easy question that takes the code that we did for question number 3, we modify it a little bit. We essentially have question number 4, so it's not going to be too bad. Now, this is something I usually get in trouble with when I'm doing my videos back for my undergraduate classes, where I say, looking at today's material, we should finish early. Now, I don't want to get you guys too excited, but I think we can finish a little bit early today, which is nice for you guys, because I know that, well, late February, early March is midterm season, so I'm sure you guys have a lot of midterms. Well, actually, I'm not too sure because you guys are graduate students. Do you guys have a lot of midterms? How's midterms looking for you guys? One? So midterms still exist in graduate school. A lot of projects, yes. So that's another thing about graduate school. Being civil, I'm not too familiar. Usually classes in civil have that one kind of final project like this course, but I heard that mechanical engineers have a lot more actual projects at the end, so maybe that's going to be true. Oh, and there's one thing I wanted to talk to you guys about this assignment real quick. The assignment you guys just did, because I got a lot of questions about it, and a lot of you guys were concerned, but there's actually a trick to it. So when we were looking at the stress at point B, all right, so point B over here, when the Poisson's ratio is not equal to 0. So when we did a Poisson's ratio of 0.3, did the stress converge at that point? It converged for deflections. I'll tell you guys that. If it didn't converge for deflections for you guys, you might want to edit your assignment before you submit it. But for the stress at point B, did it converge no matter how many elements you guys selected? So Sabrina says no. What did other people find? You guys find anything? S11? What do you guys think? Did the stress converge? S12, no. So this is one of the things I've been conflicted with because I got so many questions, and the first thing that popped into my head was this would make a great final exam question. We haven't talked about the final exam yet, but that would be a really good final exam question, is why doesn't the stress S22 converge at point B? Mechanical engineers should know this. Civil engineers, we don't do a real good job at teaching why this happens. But essentially we have this, and this might be a hint for the final exam, might not be, I don't know what I'm going to pick yet, is if we look at this free surface along the beam right here, a free surface, what's the stress at a free surface? Mechanical engineers. The stress at a free surface. Zero. So I hear 1 0. Any other takers on 0? 0, 2 zeros. You guys are correct. The stress at a free surface is 0. So the stress at B should theoretically be 0. But at the same time, we have a reaction force at B. Now, if we have a load on something, is the stress equal to 0? If I were to put a load on something, is the stress going to be equal to 0? No. So this is what happens in the finite element program, which is causing a lot of problems. In our formulations, we have a boundary condition that enforces that the stress is going to be equal to 0. But then we also have a point load that says the stress is not equal to 0. So this is actually called as a singularity. And that actually will not converge because the theoretical stress at point B is actually infinite. So every time you guys increase your mesh size, as you guys see, the stress kept going up. And that's what it's doing. It is converging, but it's converging to infinity. So you guys will actually never see the end of it. And there's been a lot of research done trying to figure out nice relationships or the theory based on that convergence. So hopefully that makes a little bit more sense to you guys. That was more or less the layman's terms explanation of it, but like I said, might make for a good exam question. We'll have to wait and see. You guys excited for the final exam? There's so many juicy things that I could ask. That's the beauty about finite elements, is there's so many different element types that I could go any way I want, really. We'll discuss more about the final exam once it rolls around, so don't worry about it too much right now. So lecture number 6 here, like we said, we addressed the theory of the stiffness matrices of these solid elements, but we said that there is some problems in the fact that we can calculate them if we wanted to, but it's not a simple calculation. We have a double integral, we have shape functions that change depending on which element you pick, etc. So the whole goal of this lecture is we're going to take what we learned for solid elements and we're going to try and simplify them, make them as easy as possible to try and code as well as to calculate. So what we're going to do is we're going to look at something called isoparametric elements. Isoparametric elements. It sounds really nice. Now, what we're going to do with these isoparametric elements is we're actually just going to attach that label onto existing elements. So we talked about quadrilateral elements. Those are our square or rectangular elements. Well, now we're going to talk about isoparametric quadrilateral elements. As you guys are going to see, isoparametric isn't so much a specific type. It's more of a way of deriving a different formulation for these exact same elements that we had before, just to make them run a little bit smoother. I'm just going to move the camera over here so I can, perfect. So when I talk to you guys, it looks like I'm looking more at the camera rather than over my shoulder, like I'm expecting an attack or something. All right, so we're going to talk about isoparametric quadrilateral elements. Now, we're actually not going to talk about isoparametric triangular elements today, but as you guys will see, the formulation of getting these is going to be the exact same as quadrilateral. Might make for a good final exam question. We're going to have to wait and see. So let's begin. I just got to click the PowerPoint. So let's go back to our theoretical quadrilateral elements. We said that, all right, if I had a quadrilateral element and I want to apply my classic theory to it, well, I have a nice equation to give me the stiffness matrix C. It's simply B transpose multiplied by C multiplied by B and then integrated over the element. Now, you guys know this from both the videos as well as the last lecture. I said that this integral really sucks, and there's going to be a way that we can take that integral and simplify it so we actually don't even need to integrate. That's going to be one of the major topics that we have today. But we said if we were dealing with a 2D quadrilateral element that has a constant into the page thickness, well, it basically simplifies into this, where we're taking t and then we're multiplying it by a double integral. Now that double integral captures the area of that quadrilateral element. So if we have a rectangular element or a square element, that integral is actually not too bad. So let's look at some scenarios for this element. Let's say that we have a beam right here and we have an element right at the corner there. Well, this actually wouldn't be too bad because if it's situated right at the origin there, let's say that the element is a square element and it has a length of 1, well, it would just be the integral from 0 to 1 in the x direction and then 0 to 1 in the y direction. So that's not going to be too bad. So if we're looking at that, theoretical quadrilateral elements, well, it's not too bad. The problem is as you guys will see in Abacus a lot, our element size is typically not constant. So what happens is if we have an element over there that's square, well, somewhere else on their beam, we might actually have an element that is rectangular. We're saying, all right, well, it's still not too bad because it's still a rectangle. It's base times height. So I can take the integral from, let's say, 0 to 4, and then the integral from 2 to 3. It's not too bad. But the problem that we're starting to have right now is the fact that this becomes very difficult to code. If our element size keeps changing throughout our beam, it becomes difficult to find a nice pattern. Finding a pattern is really the name of the game when we talk about this finite element method. Remember when we were talking about those bar elements or those 1D elements? A lot of the questions I got asked in that assignment weren't so much about the theory or the calculations. It was about trying to find that pattern, the relationship between nodes and elements. And if we start doing this where our element size is changing all the time, it becomes really, really difficult for us. Now, this is just one of the problems. The major problem that you guys will see, and this is something you guys will see a lot in Abacus, is we can also have elements that look like this. So my mechie engineers, I know that you guys love integration. How would you guys integrate that element right there? Any great suggestions? What would you guys do if that was your element? We need to find the area of that element. What happens then? Is it scaring you guys away? Complete silence? Well, what essentially happens is that our integral elements become inconsistent. So they vary on whether we have a square, a rectangle, or this distorted element, which basically makes them a big pain in the ass. And that's what we're going to try and address right now, is how can I find my stiffness matrix in the most simplistic way possible? How do we do that? Well, the answer is going to be isoparametric elements. Now, the key to isoparametric elements is this. We are going to take an element in our global coordinate system. So thus far, I've always used x1 and x2 for the horizontal and the vertical direction. But for this lecture, just to make things a little bit easier, I'm going to say that my horizontal direction is x and my vertical direction is going to be y. So just like abacus. We're going to say if this element is in our global coordinate system, it has 4 coordinate points. If we're dealing with a 4-node element, it has 4 coordinate points, x1, y1 at node 1, x2, y2 at node 2, x3, y3 at node 3, and x4, y4 at node 4. Now the key here is those points could be anywhere in the global coordinate system. It doesn't have to be aligned so that we have a square or a rectangle. They could be basically anywhere as long as we get that quadrilateral shape. And what we're going to do is this, and this is the key to parametric elements, isoparametric elements, is we are going to map this element right here into a natural coordinate system of z, which is kind of this weird Greek letter right here. It looks like an E to me, but it's called c, like xi. And then we have eta, eta, and which is going to be our new vertical axis. So we have z, which is going to be that e, and we have eta, which is going to be that n, basically. Now, what's nice about this is when we map it, there's going to be a very specific thing that we do, where we align each of the 4 nodes at very specific points. As you guys may have guessed, those points are going to be either -1 or 1. So node 1 now at the bottom left corner, it's now situated at -1, -1. Our node 2, which is at the bottom right corner, it's now at 1, -1. Looking above, we have 1, 1 for node 3, and then we have -1, 1 for node 4. Now, if we were to actually take this and throw it back into our stiffness matrix equation, this is really nice because it provides us with consistent integral limits. We go from -1 to 1 in the y direction, or sorry, the x direction, and then we go from -1 to 1 in the y direction. So it looks really nice. And as you guys are going to see later on, this will allow us to do something called Gauss integration. But that's going to be the topic of the second half of the lecture. So I'm just warning you guys that we're still not going to take this integral, but because we're going from -1 to 1, this will allow for something very special later on. But we actually have a problem. So it looks really nice, but we have a couple things to figure out. First one is, how exactly do we map these coordinates? It seems simple, right? I'm taking a distorted element, I'm transforming it into a nice square element. But how do we do that? That's going to be one of the questions. And this is going to be a problem because if we look at our stiffness matrix, we're integrating with respect to dx and dy. Now, if we're looking at the stiffness in this natural coordinate system, we can't integrate with respect to dx or dy because we're not in that coordinate system. We are now in the eta z coordinate system. So we're going to have to figure out a way to switch that integration at the end there. As you guys are going to see, it's not too bad. Another thing we have to figure out is that size effect of the element. If I were to take a really big element, let's say that the cross-sectional area of it is like 10 meters. No, we'll just go 10 units. I won't get into units. We'll just say that it's 10 units. If we look at this natural coordinate system, well, we can see that the area of that triangle is always going to be 4 units. It has a length of 2 and a height of 2. So if I'm taking something that's much bigger, an element that's much bigger, and shrinking it in my natural coordinate system, I have to take into account the fact that I'm either shrinking it, or it could be the opposite way, where let's say that my element in the global coordinate system is very, very tiny. And then in the natural coordinate system, I expand it to be that -1 to 1 sort of scenario. So we have to account for both of those things. So let's address one problem at a time. So the first one we're going to look at is coordinate mapping. So when we're mapping that coordinate, it sounds like it can be really difficult. I'm taking basically a rectangle that's distorted, and I have 4 coordinate points, and I want to transform it into a nice square. It sounds really complicated, but it's actually really easy. And this is going to be the secret to those isoparametric elements. So don't tell anyone the secret, but here's the secret right here, is that the mapping function between the coordinate systems. So if I want to go from the global to the natural, or the natural to the global, well, it's actually just based on the shape functions that we used in our traditional elements. Last lecture in our our theoretical solid elements, we found out what those shape functions are. Well, those same shape functions are going to be used now to discuss the coordinate mapping. So let's say that I had that element here. In the global coordinate system, it has the coordinates x1, y1, x2, y2, etc. And I want to go over to the natural coordinate system. Well, what we're going to do is we're going to use a function that we say x and y. So this is the function x and y right in the center there in red that's going to map between them. Now the question is, what is x and y? Well, it's actually really simple. X is simply going to be the summation of our shape functions multiplied by those coordinates. That's it. That's nice and easy. So if we had a 4-node element, question for you guys. If we had a 4-node element here, 4 nodes. I look kind of creepy when I do that, but 4 nodes. How many shape functions am I going to have? What do you guys think? 4-node element, how many shape functions? Eight. I have 8 nodal displacements, but I actually only have 4 shape functions. Shape functions are associated with the nodes, not the total degree of freedom. Because if we were to look at node 1 over here, we have degrees of freedom, U1, which is horizontal, and V1. But keep in mind that when we discuss those displacements, U1 and V1 have the same shape function. There's 4 shape functions. It's always based on the nodes. So if we have 4 nodes here, we have 4 shape functions. Hopefully you guys remember that. So in this case, if we have 4 shape functions, we can actually expand the summation for our particular element into this, where we have n1 times x1, n2 times x2, n3 times x3, plus n4 times x4. Nice and easy. Now the reason why you guys said they're 8, I know exactly why, is because you guys are thinking of this, is I'm only accounting for the x direction. What about the y direction? Well, it's going to be the same thing, where it's going to be our shape functions multiplied by our y coordinates. So it's actually going to be n1 times y1, n2 times y2, n3 times y3, n4 times y4. So maybe I misinterpreted you guys. So in total, we have 8 shape functions, but we only have 4 unique shape functions. So I think that we're actually all on the same page. I probably just misinterpreted you guys at all. All right. So this is actually going to be our transformation system. As you guys will see later on, if I were to take this x right here, and I were to sub in my shape functions as well as these global coordinates, and I were to plug in the value -1, -1, it's going to give me x1, y1. It's going to be quite magical, as you guys will see later on. But if we look at this right now, we say, all right, well, this is kind of gross. We have 2 equations. Let's try and simplify it into 1 equation. So I can get the following equation, where xy is equal to n1, 0, n2, 0, n3, 0, all the way on. And then for y, it's 0, n1, 0, n2, all the way on. And then this is going to be multiplied by a vector containing the original coordinates in the global system. So does this make sense to you guys right now? What we've done thus far? Because this is going to be kind of the key here to all these isoparametric elements, is figuring out, okay, what exactly is this mapping function? Once we do that, everything else is going to be a piece of cake. Well, mostly, as you guys will see. So if we were to look at this vector right here, we have our shape functions. And again, the secret here is that those shape functions are going to be the exact same shape functions that we used in our previous lecture. And then we have our global coordinates over here. So it's not too bad. Everything in this vector we'll actually know right off of the bat, because when we deal with an element in the global system, we're always given its coordinates. Those are something that we as the user define. And the shape functions, as you guys are going to see, they're going to be really, really nice. Really nice. And the reason why is because in our natural coordinate system here, we always have the exact same geometry. Always. So that'll make our shape functions really nice. So let's talk about those isoparametric shape functions. we said that, all right, well, we know how to determine those shape functions. But now it's really nice because if you guys remember from the theoretical portion last lecture, we defined the base of that rectangle as A and then the height of that rectangle as B, right? A and B, those are parameters that we had to change for every time we did a shape function. Well, now when we look at it, we know that the base of this is always going to be 2. So A would be 1 because it was 2A for the base and then 2B for the height. But now with this very static geometry, remember that -1 to 1, that'll never change. We can actually create really nice shape functions. So remember that shape functions, they must have a value of 1 at the node we're interested in, and then a value of 0 at all the other nodes. So if we were to do the shape function n1, so the shape function for node number 1, the shape function has to have a value of 1 at node 1 and then a value of 0 at all the other nodes. So it's going to look something like this. Now, if we were to look at n1 and we were to map it in this natural coordinate system, so keep in mind that when we're looking at the coordinate system right now, we're in the z eta coordinate system. We're not in x and y. And if we were to do that, we get our shape function as 1 minus eta multiplied by 1 minus z and then divided by 4. If you guys go back to the shape functions that we discussed in the previous lecture, and you guys were to set a and b equal to 1, this is exactly what you would get. All you guys have to do is transform x1, x2 into eta and z, and then set a and b is equal to 1. Now, I can repeat the same process, and I get my other 3 shape functions. Now, if we look at this, it's actually really, really nice, because these are now solely a function of z and eta. There is no sort of element geometry going on here anymore. Now this is nice because if our shape function is independent of our element geometry, will our shape functions change between elements? What do you guys think? If I remember at the beginning of the lecture, I gave 3 different elements. I gave a square, a rectangle, and then some distorted element. If this is the case now and our shape functions are only a function of z and eta, will those 3 different elements all have the exact same shape function? What do you guys think? All right, I got a private message, yes. Any other takers on yes? They will all have the exact same shape functions? Anyone brave this morning? All right, no one wants to be brave? I'll answer it for you guys. Yes, they will all have the exact same shape function. If we look at those shape functions there is not a single parameter that says, all right, the base of my rectangle is this, the height of my rectangle is this, nothing like that. It's simply a function of z and eta. Now, if we go back to our mapping function, we said in the last slide that we had this function right here. Well, now we know exactly what those shape functions are, which is good. And then those global coordinates, well, again, we as the user define what those global coordinates are. So our mapping function now, we can also conclude that it's going to be a function of z and eta, because the only variables that we have come from the shape functions. And if the shape functions are a function of z and eta, well, then our mapping function is going to be a function of z and eta. It's actually really nice and simple. Now, you're saying, Clayton, why are we doing this? Why are we doing this? Well, we're doing this because this is going to lead us to this right here, which is the Jacobian matrix. And this right here is going to be the real meat and potatoes of the lecture today. All right, so this right here, this is the big boy or big girl, if you guys if you guys want to consider it that. So the Jacobian matrix, this is how we are going to try to take into account the fact that we are going from one coordinate system to another, and the fact that we're taking an element that might be bigger than our natural coordinate system, or it might be smaller than the natural coordinate system, and we are either expanding or contracting our elements. It's all going to be taken into account using this Jacobian matrix. All right, Jacobian matrix, it's simple. The matrix is just J. I used a fancy script J because the regular J looked like garbage. You guys don't have to use a fancy script or anything like that. It's just the matrix J. What does this matrix look like? It's simple. It's the partial derivative of x with respect to z, then the partial derivative of x with respect to eta, and then our bottom 2 columns are the partial derivative of y with respect to z, and then the partial derivative of y with respect to eta. Now, how does this look for you guys? Is this something you guys want to be playing with? What do you guys think? Jacobian? Looks good, looks bad? hate it, love it. This Jacobian here is going to be the key. You guys are quiet. I'm scaring you guys now. It's not what I'm trying to do. This isoparametric element formulation is probably the most confusing our lectures will ever get. It's one of those things that's very confusing, but in the end, it leads us to a very nice result. And more importantly, it leads us to a result that's very easily programmable into a program like Mathematica, Python, C++, Fortran, if you guys are feeling particularly bold, something like that. Now, if we were to look at this Jacobian, it does look like garbage. I know you guys don't want to say it in the chat, but yes, this is a big pile of hot garbage. But it's actually not too bad, and the reason why is this. We're taking the partial derivative of x and y. And if we recall from our previous slide, we know what x and y are. It's something that we've defined. It's a function of the shape functions, which are in turn functions of z and eta. And then it's multiplied by the constant global coordinates. So in general, we said in the previous slide that x and y were just a function of z and eta. Now, if we were to look here, all we're doing is taking partial derivatives of x and y with respect to z and eta. So it's actually not too bad. All you guys will have to do in Mathematica or whatever programming you guys want, define what x and y are, and then just take the partial derivatives accordingly. It's not too bad. Now you're saying, Clayton, what exactly does this Jacobian matrix do? Well, let's explore it together. What this basically does is this takes a vector in our global coordinate system and relates it to a vector in our natural coordinate system. So it relates vectors in each coordinate system. In essence, it's going to be our nice transformation matrix. So if we wanted to, we can say a vector in x and y, well, that's going to be equal to our Jacobian multiplied by our vector in z and eta. Now, this isn't something you guys really need to know, but what's going to happen is we're going to use this identity here of the relationship between vectors to produce what you guys do need to know, which is this. We can use this transformation to figure out the change in area of an element after transformation. And what's going to happen is it's going to look like this, where our area between two vectors in our global coordinate system, which we are going to call dA, is going to be equal to the determinant of that Jacobian matrix multiplied by the area of their two vectors in our natural coordinate system. Now, what's nice is because if we were to say that our vectors in our global coordinate system were dx and dy, and our vectors in our natural coordinate system were d eta, dz, we get this nice relationship right here. Now, this is going to be the solution to that big problem that we had before. Remember, before we said when we had our stiffness matrix and we transform coordinate systems, well, we have to account for the fact that we're not integrating with respect to dx and dy anymore. We're integrating with respect to d eta and dz. Well, now we have a nice relationship between dx, dy, and d eta, dz. So therefore, I can take that dx, dy, substitute our nice relationship, and I get the following formula. Now, remember that we said that that formula above applied for all solid elements, right? That B transpose multiplied by C multiplied by B, then integrated, that applied for all solid elements. Well, this new relationship that we have at the bottom, this is going to apply for all isoparametric solid elements. So the only real thing that we did here is we just really attached a determinant of J. And what that determinant of J is, again, and this is going to be important, is it's going to relate those change in areas. So if I have an element in the global coordinate system that has an area of 10 units, and then I shrink it in my natural coordinate system so it has that area of 4 units, well, that change is actually going to be accounted for in that determinant of J. So how are you guys feeling so far? Are you guys understanding, I guess would be the word? Because this right here, this is the big boy right here. After this, you guys are on easy street. So how are you guys feeling? How are these isoparametric elements sitting in your stomach right now? I'm going to wait for a response because I'm so curious. Any brave takers? No? No one? So Oswald raises a good point. So this is something we're going to explore. So to answer your question, Oswald, I'm going to answer half of it. What is C? You guys in the chat, what was C? We'll talk about B in the next slide, because you're right, B is going to have some problems for us. But what is C? What does C do for us? The relationship between the stress and the strain, exactly. So is that constitutive law. So C actually isn't a function of x1 and x2. C was a function of the elastic modulus as well as the Poisson ratio. So C actually is not going to be impacted. C is going to remain C. It depends on if we select plane stress or plane strain. That's it. But you're right about B. We actually have some problems. So let's move on to our strains in our B matrix. So remember that we are doing a coordinate transformation, and this is actually going to cause some problems for us. And if I didn't lose you guys on the previous slide, this is where I'm going to lose you guys. So hopefully we don't lose you guys. Buckle up, I guess. So we said that our strain right here, we use the following formula in our theoretical version last lecture, where epsilon 1, or the strain in the horizontal direction, that was du with respect to dx. We said that the strain in our vertical direction, epsilon 2, that was dv with respect to dy. And then our shear strain, epsilon 1, was du with respect to dy plus dv with respect to dx. Now last lecture, I didn't do this. We kind of just went from this right here right into our final product. But if I wanted to, I could express this as the following, where I have a matrix here, 1, 0, 0, 0, 0, 0, 1, and then 0, 1, 1, 0, multiplied by those derivatives. So we have du with respect to dx, du with respect to dy, dv with respect to dx, and then dv with respect to dy. Again, I didn't do this last lecture, but I could have. This is kind of one of those intermediate steps. Last lecture, we were able to go right to the final answer, no problem. But now we need to take these intermediate steps, because if we were to look at this formulation right here now, we have a problem. U and v now are functions of eta and z. They're not functions of x and y. So what we're actually going to have to do is we're going to have to take these partial derivatives and find a nice relationship between taking a derivative with respect to dx and then taking a derivative with respect to dz. Something like that. How do we do that? Well, we're going to do everyone's favorite thing, multivariable chain rule. Multivariable chain rule. I know you guys are cringing just at the thought of it. I was too. I'm not a fan of calculus. Calculus is probably my worst subject I've ever taken. Partial differentials were fun for me, but calculus really slapped me pretty hard. I'm not gonna lie. But if we were to look at multivariable chain rule, it's actually a pretty nice relationship, where if I wanted the derivative of u with respect to x, well, that actually can be written as the derivative of u with respect to eta, and then the derivative of eta with respect to x, plus the derivative of u with respect to eta, and then the derivative of eta with respect to x. So I know I mixed up eta and z there. Remember, z is that e, eta is that n. For some reason in my head, I think because z looks like an e, I think it's eta, something like that, but I'm going to probably get that mixed up a lot. Nevertheless, we have a nice relationship for du with respect to dx. We can do the same thing for du with respect to dy, same thing for the other two. So dv with respect to dx and dv with respect to dy. Now, these four relationships that we have here, we can actually write them in matrix form as the following, where our matrix du with respect to dx, du with respect to dy, etc., is actually can be related to du with respect to d eta, du with respect to dz, etc., through that following matrix in the middle. So what we're going to do is we're going to take this relationship and we're going to substitute it into our vector above, and then we get our strain matrix as simply that vector full of ones multiplied by what I call that middle matrix, and then multiplied by a vector du with respect to eta, or z, du with respect to eta, dv with respect to z, and then dv with respect to eta. Now, my question for you guys, and this is the only part when you guys are coding this assignment that might give you guys some tricks. Do we know what those are? What do you guys think? If we look here, it's actually nice in the fact that we basically have two symmetric things right there. But do we know what d eta with respect to x is? dz with respect to x? Anything like that? What do you guys think? Ah, you guys are so smart. So I got some private messages too, but you guys are right. This is simply the inverse of our Jacobian transposed. So that Jacobian is actually going to play a role in two different things. Remember that our stiffness matrix now is B transpose multiplied by C multiplied by B, and then multiplied by the determinant of J. So that determinant of J comes directly from our Jacobian, but now we see that our B matrix too will also be influenced by this Jacobian. So this Jacobian, like I said, that's why it's the meat and potatoes to these isoparametric elements. Once we have that Jacobian, everything else is actually nice and simple. So if we were to continue on with our B matrix, well, at the end, we still had that vector containing the partial derivatives of u and v with respect to z and eta. So all we're going to do now is we're going to address this very last vector, and we say, all right, all we're doing is taking the partial derivatives of u and v. I know what u and v are. They are the exact same as last time. Nothing's changed. The only thing that's really changed in u and v is now our shape functions are a function of z and eta. They're not a function of x1 or x2 or anything like that. So we have functions of z and eta, and then we have our constant nodal displacements. So if I wanted to, I can go across that vector and I can write it as the following, where I have a big matrix now multiplied by our nodal displacements. And again, the reason why that nodal displacements don't change, they're just nodal displacements. They're the displacements at our nodes, which are going to be constant values. Now, the shape functions, those are functions of z and eta. So those, of course, will need to take the partial derivatives of. But it's actually nice and simple. If I wanted the derivative of u with respect to z, well, we know that u is going to be that first row in our vector above. So all I need to do is go across that row and take the partial derivative of each one of those components with respect to z. Our first component is n1. So in our matrix below, our first component is the partial derivative of n1 with respect to z. Next component is 0. So our next component in our matrix below is just going to be 0. Next component is n2. So in our matrix below, we have the partial derivative of n2 with respect to z. Nice and easy. If I want the next component, same thing. Keep in mind that when I'm looking at u, I'm still looking at that first row in that relationship above. So again, all I'm doing is I'm going down that row, and it's going to be the exact same thing, except the only difference now is instead of taking it with respect to z, I'm now taking it with respect to eta. And then I can do the same thing for our v components. So now when we're dealing with our v components, we look at the second row now in our relationship above, and then we just go across and take all the derivatives with respect to z and then with respect to eta. So it's actually not too bad at all. And this right here will lead us to our final expression relating our strain to our nodal displacements. So this right here, this is going to be our new B matrix. And then at the end here, we simply have our nodal displacements. So if we wanted to, we can write it as the following, where we have a matrix B, which is going to be basically three sub-matrices multiplied together, and then we're multiplying that by our nodal displacements. All right, so if we're looking at this, it looks like garbage. Remember the old B matrix? It was fun, right? It was just one matrix. It wasn't actually three different matrices. But this one's actually really nice. And the reason why is this. That first matrix right there, the 1, 0, 0, 0, 0, 1, will that change for us? Is that going to change between elements? What do you guys think? Is that going to change between elements? One, 0, 0, 0, 0, 0, 0, 1. Will that change between our elements? All right, who wants to take a shot in the dark? Yes or no question. Does it change? Oh, so now I get a barrage of no's. You guys are correct. It's just simply 1, 0, 0, 0. Like, what is there to change? It's just a matrix full of ones. So that's not going to change depending on any elements. Now, that matrix in the center there, with all the partial derivatives of our shape function, so the colorful matrix, will that change between our elements? What do you guys think? Well, partial n1 with respect to eta and partial n1 with respect to z, all those, will those change between our elements? I got another note. You guys are correct. That also won't change. So although this B matrix looks completely different, it's actually the exact same matrix we had before, and the only difference now is we have that little middle piece right there. Now, that middle piece, will that change between elements? What do you guys think? Will that middle piece change between elements? You guys are right. So the answer is yes. And the reason why is because that middle piece is a function of x and y. And those were a function of our element coordinates. So if our coordinates of our element change, x and y are going to change, therefore our Jacobian is going to change, and therefore this matrix will also change. But remember, our Jacobian, it's actually really simple to calculate. So it's actually not too bad that this changes, because updating it is actually not too hard at all. So remember that this middle matrix here, this basically is based on the Jacobian, which accounts for that change in the element shape between our transformations. Now, it's also the only component of B to change between similar elements. Now, why did I highlight similar? Well, similar, I mean 4-node elements. If all of our elements are 4-node or linear quadrilateral elements, this B matrix is going to stay the exact same, with the only difference being that middle matrix basically updating between elements. Now, if I were to switch to an 8-node element, 8 nodes, all right, so quadratic quadrilateral element, still not fun to say, but a quadratic quadrilateral element, will that first matrix of 1s change? What do you guys think? If I were to switch to an 8-node element, will that matrix of 1s change? Any takers? Ooh, so I got 1 yes and 1 no. The no was a private message, so you guys can't see it. So I need someone to try and break the tiebreaker. So the size says yes. Well, the answer actually for this one is no. The 1 matrix will not change. And the reason why is this. Where did this 1 matrix come from? Well, it came from our relationship over here. And if I were to scroll back, it'll even be more clear. Right here. So all this 1 matrix did was allowed us to take this vector relating strains and just swap it so that we can separate those partial derivatives. So if we're dealing with an 8-node element in 2 dimensions, are these still our only 3 strains? In 2 dimensions. Yes, so these are our only strains. So therefore, this isn't going to change. This 1 matrix will change if we shift to 3D. And the reason why is because in 3 dimensions, we have those additional 3 strains. So that's why this will change in 3 dimensions. But for any 2-dimensional case, this right here is going to remain the same. So the 1 matrix, it's still going to remain the same. There's going to be nothing too crazy about that. How about our middle matrix here, our 1 full of partial derivatives? If I were to switch to an 8-node element, will this colorful partial derivative matrix, will that change? Yes, so you guys are correct. That one will change, because in 8 nodes, remember, every node has a shape function. So if we have 8 nodes, we have 8 shape functions, so we have to account for the additional shape functions in that matrix. So that's not going to be too bad at all. But now we'll get into quadrilateral after. But for right now, we can say, all right, well, we now have our nice formula for a stiffness matrix, which is going to be that element into the page thickness t, multiplied by the double integral, both going from -1 to 1, of B transpose multiplied by C multiplied by B. So that right there is basically the exact same as before. The only difference is B is now a little bit updated. And then multiplied by the determinant of J, and then taken with respect to dz and d eta. Now this formula right here, like I said, this applies to all solid parametric elements. So if I were to give you guys a triangular parametric element, isoparametric element, you guys can still use that. The only difference is, of course, your determinant of J is going to change, stuff like that. It just accounts for things like that. So it's not going to be too bad at all. Now, when we get to our nodal forces, so remember our nodal forces are composed of two things. First is our traction vector and then our body forces. Now with our traction vector, where are we integrating over the volume of the element? Do you guys remember? For traction vectors, do we integrate over the volume of an element? What do you guys think? Traction vectors. No one remembers? That's okay. It's the Monday after reading week. You guys have midterms, I understand. So the hint is no. So if we were to look at this component here for our traction vector and compare it to what we did in the previous lecture, it's the exact same. We're not modifying that traction vector. And the reason why is because we're no longer integrating, with the traction vector, we don't integrate over the volume. We're actually integrating over the surfaces in which those, in which those traction vectors act. But when we look at our body forces, so things like gravity, rho b, those actually act over the volume. And since those act over the volume, we can apply our same isoparametric formulation to those as well. So instead of integrating over the volume, what I can do is I can integrate from -1 to 1 in a double integral, and then multiply whatever I have by that determinant of j. Again, that determinant of j will take into account that our element's either larger or our element's either smaller, something like that. So that's actually going to be nice and easy for us. And we're actually going to look at that determinant of j when we start, or we'll look more at the Jacobian once we start coding our program. The Jacobian's kind of hard to understand at first, but once I show you guys one thing in Mathematica, you guys will all be laughing going, oh, that's what the Jacobian does. That's really nice and simple, nice and easy. So if we look over here, nice and easy. Now let's talk about our quadrilateral case. Now the nice thing about our quadratic quadrilateral case is that it's going to follow the exact same process as before. We just have to make some minor adjustments because we have those 4 additional nodes. So again, quadratic elements, they have 8 nodes. So before we looked at the following elements, well, now we have this element right here. Not looking too nice. 8 coordinate points, each coordinate point containing 2 components. You guys already know it's probably not going to be too much fun. So what we're going to do is same process as before. We're going to take this in the global system and we're going to transform it into our natural coordinate system. Now the nice thing about this natural coordinate system is we're always going to keep it from -1 to 1. So our coordinate points are going to be as follows. It's actually really nice to see what's going on here. So the only real thing that's going to change, as we mentioned, is the fact that if we have 4 additional nodes, we have 4 additional shape functions. Therefore, our mapping function needs to include those 4 additional shape functions. Now, you guys may be wondering, Clayton, how do we account for those shape functions? Well, it's simple. If we were to look here, and this is why I tried to color code it, there's actually a really nice pattern. If we were to look at the x component, it's n1, 0, n2, 0, n3, 0, and it just goes on and on for however many shape functions you guys have. If we were to look at the y component, same thing. 0, n1, 0, n2, 0, n4, and that just goes on for however many shape functions you guys have. So if we were to look at this and compare it to what we had in our 4-node elements, well, we see that the first part is exactly the same, and all we did was we tacked on those additional 4 shape functions kind of moving forward. If we somehow had 20 shape functions, all we need to do is just keep expanding it. So that's one of the things I really want to show you guys is that even though these vectors and matrices start to get very big, it's actually really simple because it just keeps going on in a nice repetitive nature. So it's not too bad. So we said before also that our shape functions for a quadrilateral element were given as follows. But we said that was for a rectangle with a base of 2a and a height of 2b. But what's nice in our natural coordinate system, a is equal to 1, b is equal to 1. So all I need to do is substitute that in, as well as change x1 for z and x2 for eta, and I now get the following shape functions. Now again, those shape functions that I have in this natural coordinate system, they're independent of the element geometry, which is great for us. If we look there, it's only a function of that z and eta. which is again what we want. We want everything to be independent of that geometry. So if we move forward, we say, all right, well, the additional 4 nodes, that will change x and y. If I were to go back really quick, remember that having those 4 additional nodes, it changed our x and y because we had to account for those 4 additional shape functions. So what's going to happen is that will indirectly change our Jacobian matrix. But will the size of our Jacobian change? What do you guys think? Is the size of our Jacobian going to change? Will it always be 4 by 4 if we're dealing with the 2-dimensional case? Will the Jacobian change if we're always dealing with the 2-dimensional case? Sabrina says it'll stay the same. Yes, exactly. So remember that our Jacobian, and this is actually very easy to look at, what it's doing is it's relating the 2 coordinate systems. So in 2 dimensions, in our global coordinate system, I have x and y, 2 components. In our natural coordinate system, I have z and eta, 2 components. So in 2 dimensions, our Jacobian will always be 2 by 2. Now, if we move on to 3 by 3, we introduce that third direction. So I don't have x and y, I have x, y, and z. Therefore, when we talk about 3 directions, the Jacobian will change in 3 directions. But for 2 dimensions, it'll not change. The only thing that's going to change in our Jacobian between these elements, like element types, is going to be x and y. Because again, x and y are dependent on how many shape functions that we have. And then if we're adding those 4 additional nodes, we have those 4 additional shape functions. So if we were to account for those 4 additional shape functions, we're also going to see that our B matrix stays the same. So remember that this first part right here, because it's based on the Jacobian, this will indirectly change. The formulation stays the exact same, but those partial derivatives, as we see in the Jacobian above, change with x and y, while this will change indirectly. But coding this, it won't change, which is great for us. All we need to do is update our Jacobian. This matrix will stay the exact same. Now, this last part right here, this will change. And again, it's just like before when we talked about x and y. If we add 4 additional shape functions, well, we're adding basically 4 more partial derivatives. Nice and easy. But if we were to look here, this first part, that's the exact same as the 4-node element. So if we want to add an additional 4 nodes, all I did was tack on those terms. If I went from a 4-node element, let's say down to a 3-node element, I just have to remove 2 columns. Again, this is the nice thing about the finite element method. I either just add columns or I remove columns based on what element type we have. Nice and easy. So if we were to look at the isoparametric formulation, it seemed really complicated at first, but doing the isoparametric formulation of our traditional solid elements, it wasn't too bad. It always follows the same steps. First, we need to determine that mapping function x and y, but we said that x and y are just going to be a function of our shape functions. So that's actually not too bad at all. With that, we can go to our Jacobian, which are simply just the partial derivatives of x and y. So again, not too bad. Then we update our B matrix. So when we dealt with traditional solid matrices, we had that one single B matrix, but now we have a B matrix basically of 3 different components, but not too bad. We know everything in here. And then finally, we can solve for our stiffness matrix as well as our nodal forces using the following formula. So that right there, that's isoparametric elements. This is all you guys need to know, basically what we're doing in Abacus. There's only one trick you guys need to learn, which we're going to cover in about 10 minutes here. But then you guys will know everything Abacus does. And this is great. So this is why the first part of the course, it's really theory heavy. I'm going to be honest with you guys. It's really theory heavy. And the reason why is because when we're looking at Abacus, it's not just so much about giving you guys tutorials and saying, all right, this is how you do a concrete beam. This is how you do a steel beam. We want you guys to learn what exactly Abacus is doing in the background. And by the end of this lecture, and we'll do it, we're going to go through Abacus. You guys will know exactly what Abacus is doing in the background, which I think is pretty nice. I'm not sure about you guys. You guys might think it's pretty useless, but me personally, I like knowing what's going on in the background because this will especially happen after we're done talking about the next section. Abacus will give you errors, especially when we're dealing with complex geometry. Abacus, well, not errors. It'll give you warnings saying that this is happening right now. And after the next little section here, you guys will know, oh, that's what exactly is happening. That's the nice thing. So that's it for the isoparametric element formulation. Is there any questions about that before we go into a little bit of a break, or are you guys feeling pretty good with the isoparametric elements so far? What do you guys think? Is it too complicated? Not too bad? Go back to slide number 5. Sure. Of course. So this one? This was a direct message, guys, so you guys can't see this. Is this the slide you're talking about? Yes. Okay, perfect. So what is the question? Why is the summation here? Because this summation right here is essentially the exact same that we had for our shape functions. So x and y are dependent on the summation of our shape functions multiplied by our element coordinates. So right here we have a 4-node element, so we have n1 times x1, n2 times x2, n3 times x3, etc. If we switch to the 8-node element, well, then we have those 4 additional shape functions as well as those 4 additional coordinates. So then we would add n5, x5, n6, n6, etc., etc. This summation right here, this first part, this deals for any isoparametric element. It could be triangular, it could be quadratic, linear, anything. We dealt with the specific case here with 4-node or linear element, but this formula right here can be used for basically anything. This is the general formula, if you will. Does that make sense? Okay, makes sense. Perfect, perfect. Remember that this is the exact same thing that we did for our displacement functions. Remember that instead of x and y, which are our mapping functions, if I wanted my displacement functions, u and v, this was the exact same thing. The only difference here is instead of our global coordinates, we had our nodal displacements. So it's the exact same thing. The only difference is I'm taking our nodal displacements, swapping them with our global coordinates. Nice and easy. I say nice and easy a lot, but it must make some people cringe. I know I get cringy when someone says nice and easy and I'm completely lost. Any other questions before we take a little bit of a break, or are you guys pretty comfortable with this? The next section is actually rather simple. You guys will laugh at how easy that is, but this is the hardest part, because again, this isoparametric formulation, this is what abacus does. There is no next level. Usually in this course, we go from level to level and we work our way towards something. This right here, this is the final goal. After this, you guys know exactly what abacus or even ANSYS is doing, which is nice. All right, so there's no questions. It's 9:02. How about we meet back at 9:10? If you guys have any questions, just put them in the chat. I'm going to refill my water, but when I get back, I'll be happy to answer any more questions you guys have. Or if you guys are too shy for chat, I'm usually one of those people. Make sure you email me. I'm happy to answer any questions you guys have. That's kind of my job, I guess, technically. So don't be afraid to ask questions. There are no bad questions. Trust me, whatever question you guys may think is bad, you should see the first years. They are the experts at trying to find a bad question to ask. All right, guys. So I'll meet you back at 9:10, and we'll cover our last little bit of theory before we get into our example where we actually code these isoparametric elements. All right, I will see you guys at 9:10. Alrighty, guys, I'm back. I hope you guys are able to have a little bit of a break, use the washroom, grab some snacks. I had my last lecture. I taught 130 last time I taught. Well, actually, that's not true. I did 398. I did statics a while back, and I was given the luxury of the 5 to 6:30 at night lecture. So I'd usually say grab snacks or grab dinner or something like that. But it's kind of hard to grab snacks at 9 a.m. I'm not sure about you guys, but get comfy is, I guess, all I'm trying to say. Sorry, guys. I got a direct message. Just let me read it. So I got a good question about the shape function being an approximation when used in the mapping. How is it accurate? So one of the funny things is when we're dealing with this, what typically happens or not what typical, it's hard to explain. Let's put it this way. I'll just give you guys the exact answer without trying to get into how it happens. If I have my shape functions and I have my mapping function, so this right here, let me go back to it right here. So this right here, if is the question, how accurate is this right here, since n1 and 2, those are approximations. Is this what you're asking? How accurate is this? This is completely accurate, 100%, which is nice. So remember that if I wanted my x and y coordinate, x1 and x2, all I do is I input my shape functions, which are going to be a function of eta. So at x1 right here, in terms of the natural coordinate system, it is -1, -1. If I were to substitute -1, -1 into these shape functions and then multiply by this right here, I'm actually going to get x1 and x2. So it's actually exact when we're dealing with this right here. Hopefully that answers your question. Where the approximation parts come in, it doesn't really play a role in the shape functions. Where the approximations come in is when we're dealing with this in the previous lecture, when we said it's all approximations, it's because we're multiplying by those nodal displacements. And those nodal displacements is the part that starts to switch things up and creates the approximation. It's not so much the shape functions, if that makes sense. So another question, to solve a problem, do we need to build the global stiffness? Yes, you need to build the global stiffness matrix. Right now, we're only concerned with just finding the stiffness of one element. Because what you guys will see, and we'll discuss more about this at the end of the lecture, is in Abacus, we do two things. We define two things. One is I create basically a giant vector or giant matrix containing my node number and then the location or the coordinates of each of that node. For example, I would say node 1, so my first entry would be 1, and it has coordinates, let's say 3, -2. So my entry would be 1, 3, -2. And I go on to node 2. And I do the exact same thing, and in the end I create basically a giant matrix of all my nodes, their number, and their location. Then I go down to my element, and I create another matrix, and I say I have element 1, and it goes from node 1, 2, 3, and 4. And then if I have node 1, 2, 3, and 4, I can reference my other matrix to find out the locations, and then I can find my stiffness matrix. After we code this, and we're going to do it for one element, after we do it, it's actually very easy to see how we can obtain that global stiffness quite simply, which is one of the nice things about the isoparametric shape functions, is that the only thing that we actually need in here is going to be the coordinates of our nodes, our material relationships, so Poisson's ratio, elastic modulus, as well as that thickness into the page. But in terms of the element itself, neglecting any sort of material properties, all we really need to do is say what our coordinates of our node is, and we'll get our stiffness. Nice and easy. So you guys will see that a little bit later on, but it should be good. Does that answer your question, Oswald? Or are you pretty good? Hopefully. Yeah, no problem. So yeah, we'll code this after. So personally, I can never really understand things until I see it in action. I'm not sure about you guys. If I were to give myself all this theory, I probably wouldn't understand a thing. Usually when we implement it into a program, that's where everything starts to make sense. And I see that I have a lot of light shining on my face, so let me just close the blinds here. On a brighter note, it's nice that we have a nice sunny sky being this early. That's one of the things I like about winter semester, is that every morning we wake up at 8 a.m. It's usually a little bit lighter, which makes things, I don't know, I just find it easier to wake up when the sun's shining rather than waking up and it's dark until 10. That's just depressing. All right. So if there's no more further questions, we're going to our last little piece of our element theory, and that is Gauss integration, or it's sometimes called, or not sometimes called, the formal name is actually Gaussian quadrature. So I call it Gauss integration. I'm informal, I don't really care. And as you guys will see, this has to do more about straight math than it does the finite element method, but the results from that straight math allow us to do something very special, something that I've been hinting at for the last 2 lectures. So what I'm going to do is I'm going to call this our last modification, because essentially this is it. By the end of this topic right here, you guys will know the exact process. Abacus, ANSYS, OpenSys, whatever program you guys want, you guys will know the exact process it uses to find its element stiffness matrices, which is great. And that last piece is solving that double integral without actually integrating. So again, that's the key here, and that's something that I can't shut up about because I really don't like that double integral. I don't know about you guys. Maybe I just had a bad relationship with calculus, but I don't like that double integral. We're going to figure out a way how to actually get rid of it. So if we had our beam here, we said, all right, well, I now have a shape or an element and square. And I said that after our isoparametric formulation, we have a nice formula for our stiffness matrix. Now, if I had a distorted element on the other side, well, I say, all right, well, I still have my nice isoparametric formulation. I have a formula for that stiffness matrix. So one of the key things is once we shifted to these isoparametric elements, our integrals are always going to be the same. They always go from -1 to 1 and then -1 to 1 because we are in that natural coordinate system now. We're not integrating in the global system. We're integrating in that natural coordinate system. And this is nice because basically no matter what our element geometry is going to be, our integral is always going to be the same. And since our integral limits are always from -1 to 1, we can actually solve the integral using Gauss integration, which again, the formal mathematical name is Gaussian quadrature. All right, so that's what we're going to do here now. So let's discuss what exactly this is. So Gauss integration allows for the solving of the integral of polynomial functions without the need for integration. You're saying, Clayton, what does that mean? I don't like English. Give me math. This is the math right here. If I were to have a function f of x, and I wanted to integrate it from -1 to 1, well, instead of integrating it, I can actually express it as a summation of wi, which is going to be basically a weight, multiplied by our function at a specific point. So the specific point right here, that xi, that's what we call an integration point. Now, you guys have probably already seen this. Remember in Abacus, when you guys were probing those values of stress, one of the tabs that you guys had, if you guys were looking at elements instead of nodes, it was integration points. So that's exactly what we're going to explore, these integration points. So basically, we evaluate the function at these integration points, and then we multiply them by an associate weight. Now the question becomes, all right, how many integration points do I need to maintain accuracy? Well, it's actually nice. I'm going to give you guys a nice table right here, and this table will always remain static. It's not going to change with anything. So if you guys ever have unique scenarios, just go back to this table. So it's going to depend on a couple things. Well, actually, the number of points is going to depend on one thing, and that is the polynomial we're trying to integrate. So again, that f of x, that's supposed to be a polynomial, and we want to integrate it. Now, if our f of x is a first degree polynomial or smaller, so let's say 7x plus 1, nice linear function, that's considered a first degree polynomial. Well, if that's the case, we actually only need one integration point. Our integration point is going to be located at x1 is equal to 0, and it's going to have a weight of 2. Nice and easy. Now, if we had a third degree polynomial or lower, we actually need 2 integration points. Now, these points are going to be located at 1 divided square root 3 and -1 divided by square root 3. And the weights for these ones are actually just going to be 1. So both of these have a weight of 1. And then finally, if we have a 5th degree or lower polynomial, we need 3 integration points. So we're going to have x1 is equal to the square root of 0.6, x2 is 0, and then x3 is equal to negative square root of 0.6. And then, of course, they also have some associated weights. So w1, w3, those are going to be 5 over 9. w2, that's 8 over 9. Now, again, this comes from straight math. We don't care about math. We care about the implications or the applications of math. And that's exactly what we are going to do here. But you guys may be looking at this table and saying, all right, Clayton, well, what the hell does it mean? Personally, that's exactly what I'd be saying is what the hell does it mean? So let's go over some examples. So example 1, let's say we wanted to integrate this function from -1 to 1. So 2x plus 7. Now, what degree of polynomial is that? Question for my chat. 1. I got 1. 1. You guys all agree it's 1? All direct messages so no one else can see it, but yes, it is degree 1. So we said in the previous table, if we have a first degree or lower polynomial, we only need 1 integration point. We said that this integration point was located at 0, and it has a weight of 2. So what we're going to do is we're going to take our equation here, and instead of actually integrating it, we're going to express it as the summation of wi multiplied by f of xi. Now, that n at the top there, that's how many integration points we have. Now, if we look here, we said we only need one integration point. So our summation is simply going to be from I is equal to 1 to 1. So this actually gives us a single term. We're going to have w1 times f of x1. Now, w1 here, our weight, well, our chart says that our weight is actually going to be equal to 2. So w1 is going to be equal to 2. x1, or our integration point, is going to be equal to 0. So we're going to evaluate the function at 0 and then multiply it by 2. So if we do that right there, we have 2 multiplied by 2 times 0 plus 7, which gives us 14. Now, question for you guys, is that the exact answer? If I were to actually integrate this without doing any sort of Gauss integration, is that what I would get, 14? What do you guys think? Is this exact or is this an approximation? What do you guys think? It's a good question. Exact, yes. This is the exact solution. So this right here, this wasn't an approximation. This was the exact answer. Let's go to a different example, because if we look at that 2x plus 7, that's baby math. Everyone can do 2x plus 7. Maybe that's why it's exact. It's because it's just so simple. Let's go up a bit higher. Now we want to integrate 3x to the 4 plus 5x cubed minus 2x squared plus x minus 10. So what degree polynomial is this? All right, got a direct message saying 4. Any other takers on 4? Yes, you guys are exactly correct. So this right here is a 4th degree polynomial. So if I were to go back to our handy dandy chart, how many integration points do we need for a 4th degree polynomial? I got a direct message saying 3. Any other takers? I know it's so simple, you guys are probably rolling your eyes thinking I'm an idiot. Well, that's the other secret. I am an idiot. All right, so if we move on, you guys are right. It's a 4th degree polynomial, so it's going to have 3 integration points. So what we're going to do is we're going to express that integral as the summation from I is equal to 1 now to 3. Remember, if we had one integration point, that n at the top of the summation, that's how many integration points. So since we have 3, it's going to have a 3 at top. Therefore, this integral is simply going to be w1 times f of x1 plus w2 times f of x2 plus w3 times f of x3. Now, x1, x2, and x3, those are given in the chart. w1, w2, w3, those are also given in the chart. So if we're dealing with 3 integration points, our weights were 5 over 9, 8 over 9, and then 5 over 9. And then our integration points, x1, x2, and x3, were square root of 0.6, 0, and negative square root of 0.6. So if I were to evaluate that right there, I get negative 20.133. Now, this is a big polynomial. This is the big boy right here. Do you think that's the exact solution, or do you think that this is when this starts to become an approximation? What do you guys think? So I hear one approximate. Approximate. That was a direct message. You guys don't see it? You guys ready for the mind-blowing session of the year? This is the exact solution. So if we were to go to this table and we were to follow this table religiously, for example, if I have a 5th degree or a 4th degree, I use the proper amount of integration points, I use my proper associated weights, it will always be exact. And the reason why it will always be exact is because we're dealing with polynomial functions. If I were to introduce a radical, which is one of the questions I just got asked in direct message, so you guys can see it. If I were to use this for a radical, then it would be an approximation. And it's actually a pretty good approximation. But if we're dealing with a polynomial function, it's actually exact, which is great, provided that we use the proper amount of integration points. What do I mean by that? Well, if we had a 4th degree polynomial that we just had, And I wanted to be a little bit cheeky and say, well, you know what, instead of 3, I'm going to go with 2 integration points. Because you guys can do that. There's nothing holding you back. There's no math police coming knocking at your door. So if you guys want to do that, you can. And then as you guys will see, it won't give you the exact solution, but it'll be a good approximation. And if you guys think about abacus, when we talked about reduced integration, that's exactly what reduced integration is. Instead of using 2 integration points like I should, let's say I just used 1, something like that. But we're going to talk about that, so don't worry. So we did our examples. We're feeling pretty good about this Gauss integration, looking pretty sexy, but we have a problem. We don't have a single integral in our stiffness matrix. We have a double integral. Gauss integration says, you know what, no problem. I can take care of that. So if we're having a double integral from -1 to 1 and then -1 to 1, and I forgot to add a dy here, so I'll make sure to fix that. I apologize for that. Well, this can actually be expressed as the double summation from I is equal to 1 to n, j is equal to 1 to n, of wi times wj times f of xi, yi. Now, these integration points and the weights are going to be the exact same as the table above. The exact same. So everything in this equation is actually known. It's not too hard to figure it out. Now, what I want to do is I want to show you guys what exactly this would mean, because it's actually kind of hard to picture in 2 dimensions. So if I were to have, let's put it this way. Well, let me get rid of that. That might have been a hint. If I had a second order polynomial, right? A second order polynomial, I need 2 integration points. That comes right from the table. If I need 2 integration points, how many total integration points do I have from that equation? What do you guys think? If I have a second order polynomial, my chart says I need 2 integration points. So how many total integration points would I have? I got a direct message saying 4. Any other takers on 4? Might be 5, might be 6. What do you guys think? I'm trying to make this class interactive, as you guys can see. It's pretty hard online. But yes, I'm getting a lot of direct messages saying 4. You guys are completely correct. It's 4. Because basically we have 2 in each direction. So the first summation goes over the horizontal direction. So I have 1, 2. And then the second summation goes over the vertical direction. So I got 1, 2, and then 1, 2. So it actually looks like a square in the end. And I'm going to show you guys what exactly this looks like. And you're saying, Clayton, well, you know what? I can't exactly picture that. You're moving your fingers, but you look more like a clown than an actual instructor. Well, that's fine. Let's see if the math can show it. So if I have 2 integration points in each direction, then that n at the top of my summations is going to be 2. Now, if I were to expand this out, I get the following right here. Now, if I were to look at this, I say, well, W1, W2, again, those come directly from my table. I know what W1 and W2 are. If I were to go back to my table to you guys, and I had a second order polynomial, what is W1 and W2? What are my weights for a second order polynomial? W1 and W2. So Mahmoud, those are the integration points. I'm asking about the weights right now, W1 and W2. Yeah, no problem. 1, you guys are all correct. It's 1. So it actually makes things really nice. So our weights are going to be equal to 1. Our integration points, as Mahmoud pointed out, are 1 over the square root of 3 and -1 over square root of 3. So that actually expands to the following. And these right here are our 4 points. As we can see, we have 1 point here, we have 1 point here, 1 point here, and then 1 point here. Does that make sense to you guys? Basically, the number of integration points that we need is squared if we're dealing in 2 dimensions. So if we need 2 integration points in 2 dimensions, we need 4. If we have 3 integration points in 2 dimensions, we need 9, etc., etc. So now let's actually apply this to our personal elements. So we're going to deal with our quadrilateral elements, and we're going to call these full integration elements. We're going to discuss what exactly full integration means in about 2 seconds, but it's something that you guys have seen in abacus before. Remember when we were dealing with our element type in that box, we had the option to select reduced integration, and we said if we don't select reduced integration, it's actually called full integration. Now we're going to learn exactly what this means. So for our quadrilateral elements, we have the following equation here, and we say, all right, what exactly are we integrating? Well, this right here is going to be the function that we're integrating. We're integrating B transpose multiplied by C multiplied by B multiplied by the determinant of J. So what we're going to do is we're going to say, all right, well, we know that that function that we're integrating, it of course depends on what element order or geometric order we're dealing with. Because we know that B and J are going to change whether I have a 4-node or an 8-node element. They're going to change. So let's look at the 4-node case first. So if I'm dealing with a 4-node case, my linear element, I can't get over how creepy I look when I do that. When I'm dealing with that case, what do you think is going to be the order of that function above? B transpose C multiplied by B multiplied by the determinant of J. If I'm dealing with a 4-node element, a linear element, what is going to be the order of that polynomial that is resulted from that? Now, this is one of those things that you can't really tell until you do the math. It's too complex. But what do you guys think? I'm curious. This is just straight shot in the dark. This isn't something you guys should know. This is one thing you have to really kind of look into the math. But what do you guys think is the order of the polynomial resulting from that function? No one wants to take a shot in the dark? Not the size. So I got one that's saying that it could be a 5th order polynomial. Well, if you guys do the math, and again, this isn't a question you guys should have known. The only way you guys can really see this is if you do the math and then look at the matrix. It's actually a 3rd order polynomial, as you guys will see. The highest order that we'll have is eta and z cubed. So if this is going to be a cubic function that we're integrating, cubic polynomial or 3rd order polynomial, how many integration points did we need for 3rd order polynomial? Do you guys want me to go back to the chart? Or you guys remember? What do you guys think? It's cubic, 2? You guys are completely correct. So we need 2 integration points in each direction. So therefore our function right now can be solved by the following. Now you may be saying, Clayton, where are the weights? Well, remember, for 2 integration points, the weights are just equal to 1, so I got rid of them. So as we can see, we have 4 total integration points. Now, if I were to take our element, which looks like this in our natural coordinate system, and I were to plot those integration points, it's going to look something like this. So when you guys are in Abacus and you guys are probing those elements for values, one of the options it will give you is, do you want the value at the integration points? Now you guys know where exactly those integration points are. And this is great. So we have 4 total integration points. Now, if we were to look at the computation for this element now, we have a total of 256 computations. We have an 8x8 stiffness matrix. So as we know, our stiffness matrix is going to be 8x8. And then we have to look at that stiffness matrix at 4 integration points per, I guess, element. It's hard to describe. Element of it. You guys know where the 8x8x4 comes from? We have 8x8 stiffness matrix, and we have 4 integration points. So each, that's the word I was looking for, component. Each component of that stiffness matrix has to be evaluated at 4 separate points. This is where we get the 256 computations per element from. So this is going to be our 4-node element. And if we don't check reduced integration, it's going to evaluate that element at 4 different points. And as we said, if it's a polynomial, it'll be exact. So my question to you guys here, and this is something we're going to explore more in the example. I'm not going to give you guys the answer yet. Is that function B transpose times C multiplied by B multiplied by the determinant of J, is that a polynomial or is it a radical? What do you guys think? This is just guessing right now. I'll tell you guys the answer when we code it, and it'll become very clear. What are our initial guesses? Polynomial or radical? Sabrina says polynomial. And Sabrina might be the only one to answer. Oh, more polynomial, not polynomial. Oh, so it's going to be a bit of a civil war in the chat once we get to the once we get into the actual computation. I'll give you guys. Oh, actually, I guess I'll spoil it since you guys are both ways. It could be either or. So what happens is this: if our elements are rectangular, square, anything like that, it'll be a polynomial. So in that case, it's exact. But if our elements are distorted, so they look like those weird trapezoids, then it's a radical. So this is why when we're meshing things, I'm sure that a lot of you guys have actually done finite element in the past. But when we mesh things, we want to make sure that it is as square as possible. And the reason why is exactly that. If it's not square, it becomes a radical. And if we do a radical in here, it still provides a good approximation, but it becomes an approximation. It doesn't become exact anymore. And we're going to see that once we code our program. What we're going to do is we're going to find our stiffness matrix C, and we're going to compare it if it's a square or rectangular element, and we're going to find out that it's going to be exactly the same as the integration. But if we provide a distorted element, then it will actually be an approximation. But the approximation is pretty good. So that was our 4-node element. What about our 8-node quadratic element? So for our 8-node quadratic element, well, actually, let's ask you guys again. The guessing game is a lot of fun. Do you guys think that the quadratic is going to be cubic? Do you think it's going to be quartic? Maybe 5th order, 6th order? What polynomial do you think the quadrilateral element will result in? I hear 5th order. All right, we'll see with that. Well, so what I've seen is it's actually quartic. So if it's a quartic or a 4th order polynomial, can I use 2 integration points? Maybe I go back to the chart on this one. Oh, Oswald's right on the money. No, we need 3. Because now that we're dealing with a 4th order, we need to move up a level. So therefore, we actually need 3 integration points for this bad boy right here in each direction. So if we have 3 integration points in each direction, how many total integration points do we need for this element? 9? You guys are on the money today. You guys are looking really good. So for this particular case, if we have 3 integration points, then the n on top of our 2 summations becomes 3. What we end up getting is 9 total integration points. So what happens for this quadratic element is we know it has 8 nodes, something like this, and the integration points are going to look something like this if we were to plot them out. Remember that it's square root of 0.6, 0, and then negative square root of 0.6. So this requires a total of 2,304 computations, drastically larger than our 4-node element. So this is one of the reasons why, if we're switching between those sizes in Abacus, it starts really increasing that computation time. It's not so much as double, but more almost 10 times the computation time. Where did I get that number from? Well, remember, for a quadratic element, our stiffness matrix is 16 by 16, and each component of that stiffness matrix now has 9 integration points. So it's becoming to be quite a bit. So just some general notes on this full integration. If we use the proper amount of integration points, the proper amount. So again, for our 4-node, we said that it was cubic, so we needed 2 integration points. For our quadratic, we said that it is quartic, so we needed 3 integration points. If we use that required amount of integration points, we call that full integration, meaning that if it's a polynomial function, we will actually get the exact solution. But as we can see here, even this full integration can be computationally expensive. Now, the other thing that I want to talk about, and I've already told you guys that the super secret is this. Rectangular elements will result in polynomial functions. Therefore, we'll actually get the exact solution. However, those distorted elements, so if they have those angles between corners, those will result in radical functions, resulting in a slight loss of accuracy. Now, this loss of accuracy depends on the distortion of the element. So one of the things you guys might see is, especially if you're running plasticity analysis in Abacus, is you guys will get warnings. The analysis won't stop, but it'll say this area of your beam or this area of your pipe, whatever, it'll warn you saying that those elements are becoming highly distorted. Now, all that's doing is it's saying, hey, they're becoming distorted. Therefore, the accuracy is getting lost. So in that area, at this point, maybe take it with a grain of salt, because again, it's still able to run it, but it knows that since those elements are getting really distorted, the accuracy is going down. So that's all it's doing. Now, we also said that there was a second thing we can talk about called reduced integration. So before we had full integration, but now we can talk about something called reduced integration. The point of reduced integration is to save computational time. How do we do this? Well, we use less integration points. Simple as that. So when we had our linear elements, we said that for full integration, or to provide the proper amount of integration points, we needed 4. What reduced integration is, it says, well, you know what, instead of using 4, or basically 2 integration points, I'm going to go a level lower, and I'm only going to use a single integration point. Now, this will still work. The problem is you'll start to lose some accuracy. Makes sense. Same thing for the quadratic element. For a quadratic element, full integration requires 9 of these integration points. But you guys may be saying, you know what, Clayton? I'd rather reduce it down to those 4 integration points. It would drastically save us computation. I believe it'll go from like 2,300 computations to like, I don't know, 1,024 computations, something like that. So it's actually really nice. The problem is, of course, will result in accuracy. So although reduced integration saves computational time, in the case of quadratic element from 2,300 computations to about 1,000, it leads to a structure that is actually too flexible. Too flexible. We're going to talk about this more on the last slide. But I want to ask you guys, and this is kind of one of those funny things in finite element. Is being too flexible a bad thing? What do you guys think? Is being too flexible a bad thing? Large deformations. You guys are kind of overthinking it. Okay, so I got a direct message that's going to go on to what we're going to talk about next. But remember that when we talked about our 4-node quadrilateral element last lecture, we said based on the formulation that we're using, we had parasitic shears. And remember, we said that those parasitic shears lead to the element being too stiff. Right? You guys remember that from last lecture? Well, if we were to have an element that's naturally too stiff, and then we were to decrease that stiffness, aka making it more flexible, maybe the solution will actually be right on how it does actually behave. So that's one of those things, that this structure being too flexible, it may not necessarily be a bad thing. It might actually give us more accurate results. Because again, for a 4-node element, it's naturally too stiff. So if we make it more flexible, we actually might make it right in that sweet spot on the actual behavior of it. So it's one of those funny things. But now I know you guys are wondering, Clayton, why does it lead to something that's too flexible? Well, this has to do with its spurious modes. Or again, a lot of you guys have probably done finite element before. You guys have heard of the term hourglassing. This is something we want to avoid. So the result of a structure that is too flexible due to this reduced integration is because it has spurious modes, which basically are modes that result in 0 stiffness. That means that there are certain displacement fields that technically require 0 amount of force being applied, which makes no sense. If I were to take my clicker here and I don't apply any force, well, we know it's not just going to spontaneously start to deform, but that's what's happening in these elements. And we'll discuss the reason why. For a linear element, so a 4-node element, we actually discussed the spurious mode. We said it's actually equal to bending. So if we had our 4-node element as such, and we did reduced integration, so instead of our 4 points, we only have that single point right at the center. And we were to apply a bending displacement field, all right, a bending displacement field. So it looks something like this, or in other words, it would look something like this. This is actually a problem. Because if we were to look at our integration point right here, it's right at that transition from compression to tension. So therefore, at that integration point, there are no strains. And then mathematically, you're saying, well, if there's no strains, then there must be no applied forces. So this is where the problem starts to happen, is if we do reduced integration, we might actually activate one of these modes where we're actually going to predict 0 stiffness under some certain deformations. Now, if we were to go to the quadratic element, the spurious mode actually looks like an hourglass, and this is why we call it hourglassing. So again, if we were to do reduced integration, we have those 4 elements. Now, the hourglassing mode has the following displacement function right here. So if I were to apply all of these displacements, and this is going to be what you guys are asked for in question number 4 of your assignment, to apply this displacement to your stiffness matrix, what you guys will see is the force required to create this displacement is actually 0. It says that if I were to apply 0 force to this element, it'll deform like that, which of course makes no sense. We know it's not actually going to deform like that, but it's one of the things that we have to be aware of. The reason why, well, these points just so happen to conveniently line up where all those places where there is no strain. Make sense to you guys? What do you guys think? That was it. At this point, you guys now know everything Abacus does. Remember, when we went to modify the element type in Abacus, we basically had 3 different options. Do we want a do we want a triangular or quadrilateral element? You guys know what both of those are. The next thing it said is, do you want a linear or a quadratic element? You guys know exactly what both of those are. Now, the final mystery, of course, was, do you want reduced integration or full integration? Now you guys know exactly what those are. So if you guys are looking at Abacus from an element standpoint, you guys know absolutely everything there is for a linear elastic analysis. Now the question is, what happens when things become nonlinear? We can either have geometric nonlinearities or we can have material nonlinearities. And those are going to be something that we should start to cover next lecture and beyond. But that's it for linear elastic analysis, basically. So how are you guys feeling? Is there any questions or concerns, anything like that? What happens to U2, V2, and V2 is down here. I'm assuming this is what you're asking, right? I am missing some though. Yeah, okay. There probably is some missing. I'll just double check this and I'll modify it. But yeah, there should be some more. You're right, U6. All right, yeah, I'll go update it because you're right. It should be 16 components and I only have 12 listed. I'll fix that and show you guys. So thank you for pointing that out. That's another mistake I'll have to correct. All right, so if there's no other questions, and if, again, just put them in the chat. I'm going to go refill my water. We'll take a break. How about we meet back at 10 o'clock? And we're going to code the 4-node isoparametric quadrilateral element. It's quite a mouthful, but no, that's what we're going to do. So does that sound good to you guys? This is actually your assignment question. So depending on how active you guys are in the chat, we might be able to finish your guys' assignment question before the end of today's lecture. So again, I'm just going to go refill my water. If you have any questions, throw it in the chat or email me. I'll be happy to answer it when I get back. All right, guys, I'll see you then. All right, guys, I'm back. I don't know where my camera went to, so I can't see me. Hopefully you guys can see me. And we are going to start coding our program. So what I did is I opened up basically all the slides that we're going to need to basically solve question number 3. So I'm going to go to the assignments, and this current assignment, assignment number 5. Oh, I can't access the tab because the Zoom controls are in the way. How can I move these? Oh, I can actually just move them. Nice. I'll move them over here. All right, so if we were to look at assignment number 5 and scroll down to question number 3, it says, assuming plane strain, unit thickness, elastic modulus of 1, and Poisson's ratio of 0.2, determine the following for the 4-node quadrilateral isoparametric element with coordinates 1, 1, 3, 2, 5, 4, and 2, 5. It wants the Jacobian matrix, the stiffness matrix using built-in integration. So this would actually be from integrating it from -1 to 1, then -1 to 1. The stiffness matrix using full Gauss integration, and then the stiffness matrix using reduced Gauss integration. So that's what we're actually going to cover right now, nice and easy. And I opened up all the slides that we're going to need. We're going to need the 2 slides from today. So isoparametric quadrilateral elements, We're also going to need Gauss Integration. And then I also opened up our general solid elements, and that'll become apparent very quickly why we need that. So we're going to go back to Mathematica, if I can find it, of course. So we got Mathematica here, and then what I like to do is I just like to start clearing all the parameters, and that actually might be a little bit too big, so I might switch that. So I'm just going to make that a little bit smaller. How's that for size? Right there. Is that a good enough size that you guys can still see without being too crazy? Good size? All right, perfect. So right here, I just want to make this very clear so there's no tricks. We're going to do a 4-node element. All right, so we're not going to do an 8-node. 8-node is actually extremely simple once we figure out how to do a 4-node. We just have to modify the code in very little pieces. All right, so we're going to come down here, and then of course the next thing I always like to do is I like to say what my parameters are going to be. So if I were to come over to, oops, I need to come over here. So my stiffness matrix, let's take a look at what we need. If I were to scroll all the way down to our final expression right here, I need a couple things. The first one I can see is I automatically need that T, that thickness, into the page. So one of the parameters I'm going to specify right off the bat is T, and in our assignment it said use a unit thickness. So T is equal to 1. Hopefully there's no questions there. I'm going to come back over here. I'm going to say, all right, well, I need B. Now B is going to be a little bit complicated, so we're going to leave B for now. How about C? What is our C dependent on? What do you guys think? What parameters does C depend on? Question for the chat. E and V. Completely correct. So what we're going to do is we're going to come back to Mathematica. We need our Young's modulus. In our assignment, we said it's equal to 1. And we need our Poisson's ratio. In our assignment, we said it's equal to 0.2. Now we come back here. We actually need to input one more thing. And it's actually pretty obvious, but let's see if we can figure it out. What is going to be the key to determining this matrix B? If I come back up here, to we figure out, or down here, I guess, to where we said what B is, which is going to be this, we need a couple of things. Do I need to define anything right here? No, it's just constant values, so that's not going to be a problem. Now, when it comes to these second and third matrices, so this one right here, as well as this one in the end, they're a function of these partial derivatives, but everything can all be traced back into one thing. So one of the things is, if we look at our shape functions, we said that our shape functions for these isoparametric elements, which we have right up here, they're functions of z and eta. So we actually don't need to, we'll need to define these, but they're not dependent on the element geometry whatsoever. So we actually don't need to do anything for that over there. But what about this matrix C right here? What is this matrix C going to depend on? What do you guys think? What do we need to define that is unique to our element that is going to impact this matrix C right here? So it said dimensions. Basically, yes. So what we're going to do is we have to input the coordinate points. So that's going to be one of the key things. So what we're going to do is I'm going to create a variable. We're going to create a variable called coordinates, which is going to be my coordinate points, and I'm going to make it a vector consisting of our 4 coordinate points. Since we have a 4-node element, it makes sense that we have 4 coordinate points. So I'm going to have 4 separate entries. I'm going to just separate them each by a comma, and I'm going to input coordinate points. So for right now, let's just keep it simple. We're going to go 0, 0, then we're going to go 1, 0, and we're going to go 1, 1, and we're going to go 0, 1. So right now we basically just have a nice square rectangular element. Now your guys' assignment is not a square rectangular element, but all you guys will need to do in your assignment is basically just modify the coordinates. That's the nice thing about these isoparametric elements, is these parameters that we just defined, 4 of them, that's all we actually need. And even if we move on to a quadratic element, that's all we need. It's just these 4 parameters. And these 2 are actually based on material properties, so they almost don't even count. The only thing we need to do is define the geometry of our square or rectangle, as well as that into the page thickness. So hopefully this isn't too bad. Again, this is all we need, which is one of the nice things about these isoparametric elements. So the next thing I'm going to do is I'm going to look at this B matrix, and I'm going to try, not the B matrix, our stiffness matrix, and I want to try and get all the simple things out of the way. Our B and our J matrix, well, those aren't simple, so I'll leave those to the end. T, we already defined what T is, so T was nice and simple. What about C? If I wanted to define C right now, what's the key to figuring out what C is? What do you guys think? Remember in abacus that C is something that you guys had to specify. So you guys are right. It depends on if we pick plane stress or plane strain. And that's why I opened up our old general solid elements slides, is because if we scroll down to when we talked about C, we said that C depends on if we pick plane stress, which is going to be this one, or if we picked plane strain. Now, if we look at our assignment over here, it says very clearly that we want to assume plane strain. So right here, plane strain. So what we're going to do is we're going to take this matrix C at the side, and I'm actually just going to push it to the side here so that I can do it at the same time. And we're going to define what C is. So we said C for plane strain is going to be equal to this. So I'm going to create a section. I'm going to call it constitutive law. And I'm going to go plane strain. So this is kind of one of the things that I'm kind of helping you guys. If you guys look on eClass, I posted code for one of these problems. Now, if you guys look at this code right here, I have plane stress. So please don't just use this code, submit it thinking it's the assignment code. It's not. You guys can use this code, but you guys are going to have to modify for plane strain, because in this code right here, I used plane stress. Okay, it's just something to be aware of. But implementing it is actually nice and simple. I'll call my matrix CC. The reason why is because C by itself is already defined, so I can't use C by itself. So we're going to go CC is equal to, and basically we have a constant out in front. So what I'm going to do is I'm just going to put brackets. So we know it's going to be our Young's modulus divided by, and then inside here we're dividing by two things. The first thing is 1 plus the Poisson's ratio. So I'm simply going to go 1 plus V. And then our second one over here is 1 minus 2 times the Poisson's ratio. So I'm going to go 1 minus 2 times the Poisson's ratio. And I'm just going to put my multiplication sign over there. So this is going to be that constant out in front here. Now, if we look over here, we have to multiply it by this 3 by 3 matrix. So I'm going to multiply this into a 3 by 3 matrix. So I'm going to go 1 row, 2 row, 3 rows. And I'm going to put my commas. And I'm simply going to put in the entries of each row. So our first row is 1 minus V, V, and 0. Nice and simple. 1 minus V, V, 0. Move on to my second row. We got V, 1 minus V, and then 0. So I'm going to go V, comma, 1 minus V, and then 0. It's technically new, not V, but I don't really care. Move on to the bottom row. We have 0, 0, and then this factor over here. So I'm going to go 0, comma, 0, comma. And basically what we have is we have 1 minus 2 times V, and then all this is going to be divided by 2. So does that make sense so far? We did our constitutive law. I could put this back up because we don't really need to change that. Go back to our code, expand this. So how's that so far? All we did is we just put in our constitutive law, which is going to be our C matrix, looking pretty good. You guys happy? Thumbs up? Thumbs up? Well, I guess I can't see you, so I probably look like an idiot doing that. All right, so now if we go back to our theory, we're done with the plane stress. So we actually don't need that slide anymore. We come back here, we say, all right, well, one of the things that we're going to need is that J. Because remember that our B matrix here is heavily dependent on that determinant J. So the next thing we're going to want to try and figure out is what is our Jacobian J. Well, we have a nice formula for our Jacobian matrix. It's nothing too crazy. Partial x with respect to z, partial x with respect to eta, partial y with respect to eta, or z, and partial y with respect to eta. Now, if we look at this, we say, well, if I want to solve this, I need to figure out what my functions x and y are, right? If I want to take the partial derivative of a function, I need to know what exactly that function is. So if I were to scroll up here, well, we know that x and y are going to be equal to the following functions. Nice and easy. So if we look here, we have our global coordinates, which we actually already defined, so that's good to go. But then we're multiplying it by a vector full of our shape functions. So what we're actually going to need to do is we're going to have to create what our shape functions are. You're saying, Clayton, what are our shape functions? Well, they're right here. Nice and simple. So what I'm going to do is I'll put this back to the side. I'll put it over here, and I'm going to create my next section, which is going to be our shape functions. So since we have 4 nodes, we have 4 shape functions right here. So we know that n1, just looking at the side here, it's simply going to be 1 minus eta. So 1 minus eta. Then we multiply that by 1 minus z. And then we divide it by 4. In case you guys are wondering, where does this formula come from? Well, it's simply this formula right here. Nice and easy. So what I'm going to do is I'm just going to suppress it so it doesn't come out. I'm going to copy it, and I'm going to put it for the remaining 4 shape functions. Because if we look at these shape functions, they're almost the exact same form. The only thing that we're playing with are these pluses and minuses. Everything else is exactly the same. So I'm going to call this shape function 2, shape function 3, shape function 4. And when I go down the list of eta, it's negative, negative, plus, plus. So we got negative, negative. Well, then we got plus, and then we have plus. If I were to look at z, it's negative, plus, plus, negative. So we got our negative there. We have our plus, plus, and then we're left with our negative at the end. So what I'm going to do is I'm going to take our 4 shape functions, which we've now defined, and I'm going to just make them into basically a shape function vector. So ni is n1, n2, n3, and n4. So my question for you guys, when you guys get to the next question on the assignment, which says the stiffness matrix of an 8-node element, will you guys have to modify this section? If you guys are doing an 8-node element, will this section right here change? Yes, so I got a direct message. You guys can see it, but yes, it will change because remember, when we start dealing with an 8-node element, we have 8 shape functions. All we're going to have to do though is just add those extra 4 shape functions and then increase the size of our shape function vector. So even though it seems like it's going to be a lot more work, it's not too bad. All we have to do, add the shape functions and then increase the size of our shape function vector. So if we were to go back over here, we need to find what x and y are. So if I were to go up here, well, I said that x is simply going to be the summation of our shape function I multiplied by xi. So in expanded form for these 4-node elements, it's going to be n1 times x1 plus n2 times x2 plus n3 times x3 and so on and so on. So what I'm going to do is I'm going to create these right now, and I'm going to call this section our coordinate mapping. So coordinate mapping section. So what we're going to do is we're going to say that our coordinate map, I gotta make sure I'm spelling things right. It's simply going to be a vector. Now, if we look down here, we said that we wanted to make our vectors simply x and y. So what I'm going to do is I'm going to say our coordinate vector is equal to x and y. But I haven't defined what x and y are yet. But it's actually really simple because we're going to come down here, say x is equal to, and if we look here, x is simply the summation of our shape function multiplied by the coordinate at that point. So what I'm going to do in Mathematica is I'm going to use our summation command. Now this is nice because once we change our amount of shape functions, all this right here, this is basically going to remain unchanged. If you guys want to and don't want to use the summation command, you guys can manually go n1 times x1 plus n2 times x2, etc. But it makes the code a little bit harder to modify a little bit later on. So again, we're going to use our summation command. And again, we're multiplying our shape function I. So what I'm going to do is I'm going to go ni. And we're multiplying that by our x coordinate at I. So what we're going to do is we're going to multiply this by our coordinate of x at I. So here's the thing, is we're going to go 1 comma I. Because remember that if we, actually, sorry, it should be the other way around. I comma 1. And the reason why we're doing that is because we're making sure that we're only getting this first component. If I were to go 2 right here instead of 1, well, what that'll do is that'll actually take in our y components. So basically the I ensures that we go from this coordinate to this coordinate to this coordinate to this coordinate. And the 1 right here ensures that we are always picking the first entry, or in other words, we're picking that x coordinate. Now, so I want to take this summation. Now we're doing it over I equals 1 to n. So if I come over here, we know we're going from I is equal to 1 all the way until n. Now what is n in my 4-node element? What do you guys think? What is going to be n in our 4-node element? So I got another private message saying 4. Any other takers saying 4? I got another 4. You guys are 100% correct. Correct. I was going to say correct and right at the same time. Correct. You guys are 100% correct. It is 4. Now my question, when we go on to question number 4, when we're dealing with an 8-node element, what is going to be n for an 8-node element? All right, I got a direct image saying 8. You guys are completely correct. So when you guys are modifying this code, again, it's actually very simple to modify it. All we're going to have to do is just switch this 4 to 8. Now, what's nice about this too is we can take this exact same code that we made for x, and we can do the same thing for y. So we're going to switch x to y. And remember, y is simply the summation of our shape function, same as above, but instead of multiplying by our x coordinate here, we are multiplying by our y coordinate. So instead of going from I comma 1, we are now going I comma 2. And the reason what this will do is this will start picking up our second entry in each one of these vectors, which is going to be our y component. So at the end here, if I were to go my coordinate map and run it, I simply have my function of x and y. Nice and simple. So one of my questions for you guys is, and I'll zoom this out right here. So we now have this coordinate map, and one of you guys were talking about accuracy. So right here, in terms of eta and z, we have this coordinate point -1, -1 in our natural system, right? -1, -1 in our natural system. And what this coordinate maps to is our first node over here, which is x1 comma y1. Now in Mathematica here, we define that first node as 0 comma 0. So if I were to take my coordinate map and I were to substitute z approaches -1 and eta approaches -1, and I were to run it, I get my coordinate point 0, 0. Now let's go back to the PowerPoint, and I'll actually make this a little bit bigger. Let's go back to the PowerPoint. What about this coordinate over here? This coordinate 3 in our natural coordinate system is always going to be 1 comma 1. Now what happens if I map it to this third node over here? Well, we said in Mathematica that our third node is equal to 1 comma 1. So if I were to switch this in our natural coordinate system to 1 comma 1 and run it, I get 1 comma 1. Pretty amazing, isn't it? So if I were to switch this to -1 and -1, go back to that first node, and I were to switch our first node to, let's say, 0.5 or 0.4, it doesn't really matter, and I were to run it, I get 0.4 comma 1. So this shows you guys that this is 100% accurate, this mapping function. So hopefully the mapping function itself starts to make more sense now. All we need to do is we map our two coordinates, or sorry, we map our nodes together. We're always good to go. So that's going to be our coordinate mapping. Any questions about that? And I'm going to change this back to 0. Does that make more sense to you guys now? This coordinate mapping function, what exactly it does? I'm hoping so. Hoping so? Maybe not. But now that we have x and y, we can move on to the next big boy, which is our Jacobian matrix. Remember, we said that this Jacobian matrix is really going to be the key to solving everything. So if we were to go back here and we were to scroll down to our Jacobian, it's actually not too bad. We're going to use the table command just like we would a displacement gradient. And all we're doing is we're taking partial derivatives with respect to certain things. So we're going to take the partial derivative of x with respect to z, and then with respect to eta. And then we're going to take the partial derivative of y with respect to z, and then with respect to eta. So what I'm going to do, first of all, because I'm taking the partial derivatives with respect to z and eta, is I'm just going to create a variable called natural coordinate system, and this is simply going to be z and eta, just so that I can actually use my table command. If I don't specify a variable of what I'm trying to take the differential equation to, it becomes a little bit more difficult. Because of this, I can actually create my variable, which is going to be my Jacobian here, and again, we are going to use our table command. So what we're doing in this table command is we're going over all those derivatives that we want to take. First, we want to take the derivative of x with respect to the 2, and then we want to take the derivative of y with respect to the 2. So what I can do here is I'm saying, all right, well, I want to take the derivative, and what I want to take the derivative of is my coordinate map of I. Remember, my coordinate map is simply this right here. So if I is equal to 1, it's going to take the derivative of x. If I is equal to 2, it's going to take the derivative of y. So hopefully that makes sense. And what I want to do is I want to take the derivative of that, and this should be actually in here. I want to take the derivative of that coordinate map, so the derivatives of x and y with respect to z and eta. So I'm going to take the derivative with respect to our natural coordinate. I'm just making sure I spell it correct. And we're going to do that with j. So this should be nice and easy now, because what we're doing is if I is equal to 1 and j is equal to 1, basically I'm taking the derivative of x with respect to z. If j is equal to 2, then I'm taking the derivative of x with respect to eta. And then once I goes to 2, then I'm taking the derivative of y with respect to z, then derivative of y with respect to eta. So hopefully that makes sense. The problem is in my table command, I didn't specify my limits for I and j. So if we look at I is going to go from 1 to what? What's I going to go to? What do you guys think? What is my I going to go to? I is equal to 1 to what? A lot of messages saying 2. You guys are completely correct. And it's very easy to see because we're doing the coordinate map of I. So basically we're going over our coordinate map vector. Since we only have 2 components, it's going to be from 1 to 2. But that's just for our coordinate map. We also have to specify what j is. So if I were to go to the side, we know that j is going to go from 1 to 2 as well. Again, because we're going over the size of this map, we're going to have this as follows. Nice and easy. Or at least I'm hoping so. So we have our Jacobian j right now. It's good to go. Actually, I'm going to run it. Now, I'm going to ask you guys really quick. And this will be kind of one of those mind-blowing things. Do you guys know what j is? I didn't run anything yet. I didn't do any sort of analysis. Do you guys know what j is? Do you guys need to calculate j in this case if we're dealing with this element right here? What do you guys think? Who knows what j is just by looking at what our element is right here? All one? Nope. Good guess, though. Very good guess. Let's run j, and let's just see what j looks like. So I'm going to suppress that, and we're going to run j, and we're going to throw it into matrix form to see what it looks like. Oh, it's all a function of eta. Yeah, no, that should be correct. Natural coordinate j. Okay, yeah, so we'll go back to j. As you guys will see, we have to specify the points later on. So j depends on the points. All right, so I'm going to come back to that. J will be fun later on. I'm forgetting a step. So we have j. So if I were to go back over here, we are good to go. We're going to do j after we're done the integration, as you guys will see. So we're going to go back to j, and we said, all right, now we know what j is. And now that if we go back to our formula here, I now know what c is. I know what t is. I now have my j, so to determine a j is going to be a piece of cake. The only thing that we have left is actually this B matrix. All right? And in this case, the B matrix is basically going to stand for bitch matrix because it's not too much fun to code in. As we can see, we have a lot to really throw in. So what I like to do when I code this is I throw it as 3 separate components. This will be my component 1, this matrix of 1s. This will be my component 2, and this will be my component 3. And then I simply multiply them all together to get it. So what I'm going to do is I'm going to come down here. I'm going to create a section called my B matrix. And what we're going to do is as follows. We're going to simply just go through all 3 of those components. So I'm going to call the first one component B1. And if we look over here, back in our theory, it's simply a matrix of just 1s and 0s. So we got 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0. So that one, hopefully you guys shouldn't have trouble with. So I'm going to create a matrix. It's going to have 3 rows, just like that. So I'm going to separate them with commas. And we said our first row is 1, 0, 0, 0. Second row is 0, 0, 0, comma 1. And finally, we have 0, comma 1, comma 1, comma 0. If I were to run this, nothing too fancy. It's just that. So what we're going to do is we're going to come down here now, and we're going to specify our second matrix. Now, if we look at our second matrix here, it's a bit more tricky, right? It's a bit more tricky. And if I were to come up to here, we said that this matrix, or the components of this matrix, they actually depend very much so on the inverse of our Jacobian transposed. So what I'm going to do is before I define this matrix right here, I'm going to figure out what exactly this is over here. So what I'm going to do is I'm going to come back up here and I'm going to simply put J inverse, even though we're also transposing it, this is going to be equal to the transpose of the inverse of J. Very, very ugly, isn't it? But now that we have that, basically what this matrix is right here that we are going to obtain, let me just delete this so we don't get an error really quick. If I were to run this matrix right here, and I'll throw it in matrix form so you guys can really see. What these four components are essentially these four components right here, and then these four components right here. So all we're doing is when we fill out this matrix, all we're doing is we're going to specify the values as we go along. So since I have this matrix, I know that the first component of my big matrix is simply going to be component 1, 1 of this J inverse transpose. So what I'm going to do is I'm going to go B2. We know that B2 is equal to a matrix that has 4 rows. So 1, 2, 3, 4. I'm going to separate each one of these by commas, just like this. And I'm simply going to go down the row. So what I'm going to do is I'm going to put this on the side. We'll go back over here. And I guess this right here should be enough to show you guys. Maybe I'll zoom in a little bit. So we're going to go just down the rows. So this right here, our first component of this B matrix is actually going to be the first component of J inverse. If we move on to the second component, this is component 1, 2 of J inverse. So what I'm going to do is J inverse 1, 2. Moving on, next component, well, that's going to be 0. And finally, the third component, that's also going to be 0. So this is going to be the first row. Our second row, we can see that this is going to be component 2, 1 of J inverse. So I'm going to go J inverse 2, 1. Our second component is component 2, 2 of J inverse. So J inverse 2, 2. And then the next two are going to be 0. And what we're going to do is we're just going to fill in the remaining rows. So if we look at the third row, first two components are all 0. So I'm going to go 0, 0. Our next component right here is going to be the first component of J inverse. So I'm going to go J inverse 1, 1, and then we just kind of go on from there. So this is going to be component 1, 2 of J inverse 1, 2, just like this. And finally, our last row, which is 0, 0, and then we have J inverse 2, 1 and J inverse 2, 2. So does that make sense to you guys? This is one of the ones I will ask you guys if this makes sense to you guys, because this is the only real part of this matrix that can get really yucky. So what do you guys think? Is B2 not too bad? I'm hearing all good. Good, good, good. Can I show it again? All right, so this right here, this matrix, this 4x4 matrix inside of the bigger matrix, this is essentially equal to this matrix J inverse. So when I'm going out through the rows of the big matrix, what happens is this component here, this is actually equal to the first component of this matrix. So actually, let's show it here. So this component right here, this is equal to this component right here. This component right here, so this second component, this is equal to this component right here. This third component here is equal to this third component here. And then finally, this component here is equal to this component here. So now does that kind of make sense? And then the same thing is repeated. If I were to compare this matrix right here to this one down here, these are the exact same thing. The exact same thing. So instead of putting the zeros at the end as I did on the top, I just put the zeros at the beginning. So that's going to be it for B2. And B2, again, that's usually the one that sucks the most. So I'll delete that. And if I were to run this, I got a problem somewhere. Typically how it goes. Inverse of J. Oh, it's because I did matrix form. So this is one of the things too, is this is a code problem that I fall for all the time, and you guys may have caught it too. If you were to throw something into matrix form, it basically takes this right here and changes it more to a display than a variable.
So what we actually need to do is get rid of the matrix form. We do that, we're good to go. It's basically saying that you're trying to take entries of a picture, which makes no sense to Mathematica as well as to me. So we're going to finish it off with B3. So if we're going to go back to our notes, we'll go over here, zoom out. We're going to scroll down. We said that B3 is going to be these partial derivatives. Now what we're going to do to make our lives really, really easy is we're just going to put it in a loop. We're going to use something called a do loop, which is basically the same as a for loop, except it doesn't require as much punctuation, if you will. So if we look here, we see that we have partial n1 with respect to eta, or with respect to z, and then we have partial n1 with respect to z. We have partial n2 with respect to z, and then we have partial n2 with respect to z. As we can see that this first row here is the exact same as this third row. The only difference is this is offset by 1. I'm hoping you guys can see that. All the derivatives in the first row and the third row here, they're always with respect to z. And it's always going to be n1 with respect to z, then n2 with respect to z, then n3 with respect to z. So what we're going to do is we're going to create an empty table full of zeros, and then I'm going to create two loops. My first loop is going to throw in all my partial derivatives with respect to z, and then my second loop is going to throw in all my partial variables or partial derivatives with respect to eta. So that's all I'm going to do. So the first thing I'm going to do is I'm going to say that B3 is equal to a table full of zeros, and this is going to have a rather unique size. So we're going to go I from 1 to 4. This is the rows. As we can see here, we have 4 rows, and then we have 8 entries, or sorry, 8 columns. So then I'm going to go over here, we're going to go j is equal to 1 to 8. So if I were to run this really quick, I get this. Well, let's throw it in matrix form just to make it look a little bit better. We get this right here. Now my question to you guys, if I'm doing this for an 8-node element, will I equals 1 to 4 change for an 8-node element? What do you guys think? Is that part right there going to change from an 8-node element? Let's look at the formulation. Basically, am I saying, do I need more rows if I'm doing an 8-node element? So some people said yes, some said no. It is no. Remember that these don't change. These are just, the rows are simply the partial derivatives. What's going to change is the columns, as you guys pointed out. So as we can see, we have 2 columns for n1. Oops. We have 2 columns for n2, 2 columns for n3, 2 columns for n4. So if we have n5, n6, n7, and n8 in the case of the 8-node element, we just keep adding columns. So that first part's actually not going to change. This second part is going to change. This will go from 8 to 16. So we're going to have something like this for our 8-node element. But right now we're just going from 1 to 8. So again, as you guys have seen, all we did was we create basically an empty matrix of the appropriate size. But now we're going to use a loop to kind of fill that matrix. So what I'm going to say is that the entry of B, or B3, I'm going to modify the entries. So one of the things that I said here is that this entry right here is going to be equal to this entry, which is always going to be equal to partial I with respect to eta. All right, partial I with respect to z. So we're going to say that this entry is going to be equal to a second entry, and we're going to discuss what those entries are. And we said that this is always going to be equal to the derivative of ni, ni with respect to z. So, and we're going to figure out what these indices are going to be. So again, we're going always a partial n with respect to z. And it's always going to be this entry and this entry, then this entry and this entry, and this entry and this entry. So this is one of the things that came from your guys' quadratic elements, or quadratic bar elements, as you guys did in, what was it, assignment 3? Assignment 3, you guys remember that? How we did the code for linear elements, and then you guys had to do the code for quadratic elements. No one really liked it. Well, that's where it's going to come into handy. So if I have this type of pattern where it repeats every second indice. Do you guys remember what the pattern is in terms of I? Basically, what formula can I throw in that if I were to go I equals 1, 2, 3, 4, 5 gives me 1, 3, 5, 7, etc. Do you guys remember? What could I throw in to give me 1, 3, 7? I plus 2? Not quite. I plus 2. So let's remember, we're going from I equals 1 to whatever. So if I were to throw I equals 1 into I equals plus 2, basically we're skipping every second step, but then that won't work once we start getting into this entry. Remember that the code that we put in for this one also has to work for the code in this third row. So that's where it's going to get to be a pain, is I'm trying to do both of these rows at once. Now, this is one of the things that I'm trying to do both of these rows at once. If you guys want to do each row separately, you guys can go ahead. So that's kind of up to you guys. But what I like to do is I want to try and do both of these rows at once because they're basically the same. What the pattern is it's actually going to be 2i minus 1. So what we're doing is we're taking this first entry here, and the first entry is always going to be the first row. So what I'm going to do is I'm going to go 1 comma, and this will mean it's always the first row. Now I want every second entry of that first row. So I'm going to go 2i minus 1. Now we said that this entry right here, if I were to go back to the theory, this entry right here, it's always going to be equal to this entry. Now this entry is in the third row. So we're going to go B3. This time we're going in the third row. And instead of it being 2i minus 1, we can see that it's offset by 1. It's offset by 1. So instead of going 2i minus 1, in this case, I just go 2i. So hopefully that makes sense to you guys. Because now that I've done this, I can loop this from I equals 1 to 4. Basically, this will go over and give me all of my entries. So I'm going to suppress that. And if I were to write B3 in matrix form, as we can see, I filled in this one, this one, this one, this one, as well as this one, this one, this one, and that one. Does that make sense to you guys? Hopefully. Again, I was just trying to do 2 rows at once. If you guys want to do I plus 1 and do 1 row at a time, you guys can definitely do that. I'm just trying to tackle 2 rows at once. Hopefully that makes sense. So those are all the derivatives with respect to z, all right, xi. So what I'm going to do is I'm going to copy this exact same code, throw it down here, but now instead of taking it with respect to z, oops, I opened Dropbox by mistake. So instead of taking rows 1 and 3, which are respect to z, I'm going to look at rows 2 and 4, which are the exact same thing. The only difference is now it's with respect to eta. All right, so we're going from z to eta. So at the end here, this partial derivative at the end, instead of z, we're going with respect to eta. Now again, this right here impacts rows 2 and row 4, but that's the only change. It impacts rows 2 and 4 rather than 1 and 3. So I come back to my matrix here and say, all right, well, instead of row 1, we're impacting row 2. Instead of row 3, we're impacting row 4. So if I were to add that in, I now have everything I need in that matrix. Does that make sense to you guys? Hopefully. Thumbs up, thumbs down. How you guys feeling? What do you guys think? Hopefully it makes sense. You guys are too quiet today. Scaring me. And that's basically B3. So if we have B3 right now, we are good to go. After we have B1, B2, and B3 that we now have, if we were to look back over here, B1, B2, and B3, to get B, all I simply do is just multiply them together. So I'm going to come down here, and I'm going to say my B matrix is simply going to be B1 multiplied by B2 multiplied by B3. Nice and simple. So if I were to throw this into matrix form, we can run it, and as you guys can see, it's really, really, really ugly. Really ugly. And this is why we do the finite element method through a computer. We don't ever try to do it by hand. That's just asking for trouble. Now this is actually perfect. We're basically at the end, because if we look at our stiffness matrix, we need T, which we have. We need B twice, which we now have. And we need C, which we have. And then we need our Jacobian, which we also have. we have everything that we need. So what I'm going to do is I'm going to come down, I'm going to create a new section, and we're going to call this the stiffness matrix section, because now we're going to look at the stiffness matrix. So what I'm going to do to make my life simpler is I'm going to look at this, I'm going to define all of this right here, all this garbage, into just one variable, one function, which makes it really nice for me. So what I'm going to do is I'm going to put int function, so my integration function. We know that this is going to be the transpose of b multiplied by c multiplied by b again. And what I'm going to do is I'm going to put this in brackets because these are all my matrices. And then we're multiplying this by the determinant of j. So this is the actual function that when we try and find our stiffness matrix, this is what we're going to want to integrate. So if I were to throw this in matrix form right now, we get this. And whenever you get this in Mathematica, it basically means have fun. This thing is so freaking large. And that's what we have right here, large output. It doesn't mean anything's wrong. It's just meaning it's so big. Now, with that integration function, we basically have three different approaches that we can use. The first one is if we were to actually take this double integral. We can go from -1 to 1 and then -1 to 1 with respect to z and then with respect to eta. So what I'm going to do is I'm going to go ke, and this is, again, it just comes from the direct integral. We know it's going to be our thickness t multiplied by the integral of our integration function. And then we're integrating this with respect from z from -1 to 1, and then with respect to from eta from -1 to 1. So this is the actual thing that we're trying to avoid in Gaussian integration. Now, when we're dealing with decimal numbers, so since our v is in a decimal format, all this down here is going to be in a decimal format. To make the integration more smooth in Mathematica, we switch our integrate function from just simply integrate to n-integrate, which basically means numerical integration. If you guys do the regular integrate function, you guys actually might get some errors because the algorithm used in the integrate function is based on those fractions. We don't have fractions, well, things get a little bit messy when we start dealing with these large integrations. So if I were to suppress this and go ke in matrix form, we get our 8x8 stiffness matrix, exactly as expected. Exactly as expected. 8x8, not a problem at all. Now we come down here and say, well, instead of finding it like that, through that actual integration, in our second lecture, or second topic, we said, well, instead of doing that, we can use Gaussian integration. So right here, all we're doing is instead of taking the integral from -1 to 1 and then everything in this integration function, we can simply go down here and say, well, we can just evaluate this function at 4 different points and then add them together. Nice and easy. So what I'm going to do is I'm going to define my integration points for both z as well as eta. So I'm going to go z set, and this can be equal to my 2 integration points over the horizontal domain. So my first one is 1 divided by the square root of 3, and my second one is -1 divided by the square root of 3. So this is integration point 1, integration point 2 for the horizontal direction. Now what I want to do is I also want to create these integration points also for the vertical direction. So instead of z, we are now dealing with eta. All right, so hopefully that makes sense to you guys. So I'm going to suppress these. And now that I've defined my integration points, I can come down here and define my stiffness matrix. And I'm going to call this one K full for full integration because that's what we're dealing with. This is going to be equal to our thickness T times the summation now, the summation of our integration function evaluated at all of those points. So what we're going to do is it's going to be equal to our integration function, specifically when we know that we want z to approach z set of I. I'll put this outside. And we also want, oops, not outside, got to put this in here. We also want eta to approach eta set of j. So basically this evaluates it at, well, let's put it this way. This is the best way to look at these summations. If I is equal to 1 and j is equal to 1, then basically we are looking at this function when z is equal to 1 over square root 3 and eta is equal to 1 over square root 3. Now let's say I goes to 2 and j stays 1. Well, then we are looking at our integration function when z is negative 1 over square root 3 and eta is still 1 over square root 3. So hopefully that makes sense to you guys. So our limits here are just going to be from 1 to 2 because those are the size of our z set and our eta set. So we're going to have j equals 1 to 2. And that's how we find our stiffness matrix for full integration. So if I were to come down here, let's just go ke/matrix form, and we'll go k full/matrix form. We get something like this. Oh, it's because I did an uppercase K. Looks pretty ugly. Oh, it's because I didn't do the double slash. Losing my mind here at the end. As we can see, 0.509259, 509259, 173611, 173611, they are exactly the same. So does that make sense to you guys for finding the stiffness matrices so far? We're going to look at something else really quick. What do you guys think? Is that not too bad? All good? Yes, yes, perfect, perfect. So now we're going to go and we're going to look at the reduced form. So k reduced. So reduced integration. Again, it's going to be t times something. Now in reduced integration, how many integration points do we need? 1. What were those integration points? So if I were to come back here, oh, sorry, we're now in the Gaussian slide. So if we're dealing with one integration point, how many actual points are we evaluating our function at? Remember, if we had 2 integration points, we evaluated our function at 4 different locations. If we had 3, we evaluated at 9 locations. So if we have 1 integration point, we are looking at only 1 location. Now, what are the coordinate points of that location of our function? What do you guys think? What are going to be the coordinate points? So for example, when we had down here, we had our coordinate points as 1 comma square root of 3, etc. You guys are right. So I got a lot of direct messages. Oh, some were actually to everyone. It's going to be 0, 0. So what we're going to do is we're going to multiply this by our int function. And is that how I spelled it? No, I just had it like this. Specifically when z approaches 0 and eta approaches 0. Now, if I were to run this really quick, it's actually wrong. So let me just suppress it. And I'm going to go k reduced in matrix form. I'm going to run it. And as we can see, it's way off. Way off. 0.5, 0.09. So that's way off. And I told you guys, this right here is actually wrong. So I'm going to come back here, and I'm going to go to this slide. What did we forget to do for the reduced integration? And I'll give you guys a big hint. When we figured out for two integration points, we had our function, but it wasn't just our function. It was something else. Sabrina's right, weights. So for 2 nodes, or 2 integration points, our weights are always 1. If we go up to our table, it's always 1. 1 times 1 is equal to 1. Nothing really changes. But if we use 1 integration point, our weight is actually 2. Our weight is actually 2. So when we come down to this integral here, even though we're going from 1 to 1, so f is 0, 0, we need to multiply w1 times w1. So what we actually need to do is we would technically go 2 times 2. Weight 1 and the other weight. So the weight in the horizontal direction and the weight in the vertical direction. So if I were to run that right now, we see that we get this. So it's still less accurate, but at the same time, the computation time for that is extremely small. Extremely small. So this is when you guys have to try and find that trade-off between computation time and accuracy. So hopefully that makes sense to you guys. Now the last thing that I want to do with you guys is we're looking at this right here, and actually I'm just going to exit out of this, and I have the exact same code over here. So this was the code that I provided you guys on eClass. Okay, so this is the code that you guys have. So this one right here is plane stress. So in your assignment, change it to plane strain. But what I want to do is I want to look at what happens when our coordinate, or sorry, our element is not actually rectangular. So this element right here, if I were to run it, scroll down, this is what our element looks like right here. All right, this is what our element looks like. Looks pretty gross. So what happens here in this case is, as we can see, our stiffness matrix for actual integration and our Gaussian integration, it varies a little bit. So this is what I was saying. If we have a rectangular element or even a square element, our actual integration and our full Gaussian integration, they're going to be the exact same. But once our element is distorted a little bit, or in this case a lot, as we can see, they do not perfectly match, because again, this is now dealing with a radical rather than a polynomial function. Does that make sense to you guys? Hopefully. That's something important to realize later on. All right. So there's another little trick, and I'll email you guys this trick because I'm honestly forgetting what I'm missing, but it's very easy to tell what our Jacobian is going to be. And I can't believe I'm forgetting this trick. I was looking at it before. I'm thinking, oh, this is so nice. So I'm going to send you guys something to show you guys that trick with the Jacobian. But in terms of pure math, this is all you guys are going to do for your assignment. So just to make sure the actual integration is also not exact. So the actual integration is exact in terms of the integration. The problem is our approximation function is what leads to the errors, basically. So if we had a 4-node element, remember that we are approximating it using a linear approximation. And that's where the accuracy starts to kind of go away a bit, because we cannot fully capture the behavior of the element just by using a linear approximation between nodes. The integration itself is just fine. It's simply just integration. But yeah, the accuracy part deals more with the element geometric order. So, perfect. Hopefully that makes sense to you guys. You guys good? Wonderful. So that's it for the lecture. I know I wasted 4 minutes of your time, and I also made the bold claim of letting you guys, like, being done early, which clearly didn't work whatsoever, so I apologize for that. I know that you guys are busy with midterms and stuff like that, so I'm trying my best not to keep you too much now, but on the bright side, you guys know absolutely everything Abacus does with elements at this point. So from now, we can actually get into the fun stuff. So if we were to go back to E-class, we are now done with our element types. We're going to start talking about the Newton-Raphson method, which basically starts to look at how we can solve this system when there's nonlinearities. Nonlinearities turn everything into a big shit show, as you guys are going to see. So we're going to learn how to solve the system using Newton-Raphson method, and we're going to talk about different types of nonlinearities such as material plasticity, contacts, instability, stuff like that. So that's it for today's lecture. I hope you guys learned a little bit of something. If not, I'm sorry for wasting your time. That's not what I'm trying to do. But yeah, that's it. So I'll stick around for a little bit if you guys have any questions, but if not, have a wonderful day and don't stress too much about midterms or assignments or anything else in general. Just live a happy life. Enjoy yourself. You guys deserve it. You guys are hardworking students.